Why do some cosmic radio bursts repeat while others fall silent? How can massive stars vanish without a final blaze? Late on a clear night, beneath a moonless sky, the Milky Way stretches overhead as a misty river of stars. In its soft glow, you feel both wonder and mystery. Our galaxy holds more than 100 billion stars, each one a distant sun that might host worlds and secrets beyond imagination. Yet for all we've learned, the night still keeps many of its secrets. In that darkness, there are whispers of the unknown, subtle hints and flickers that remind us how much remains to be discovered. For centuries, humans have gazed upward and charted the heavens, finding order in the movements of planets and the patterns of constellations. But every so often, something truly unexpected lights up the sky. A star might dim when it shouldn't. A brief flash of light might flare and vanish, leaving observers puzzled. Or a strange signal may crackle through our radio telescopes with no clear source. These are cosmic riddles, gentle reminders that even in an age of great knowledge, the universe still holds surprises. They spark our curiosity and beckon us to explore deeper, setting the stage for a journey into mysteries that science has yet to fully explain. Imagine watching a familiar patch of sky when, suddenly, a new light flickers into view, a spark where nothing was before, shining for just a moment and then gone. Or picture a radio telescope quietly scanning the stars when it catches a sudden burst of static from deep space, a transient signal that flares and fades before you can blink. These fleeting phenomena, cosmic flickers that by all logic shouldn't be there, have become one of astronomy's ongoing puzzles. One such mystery arrived in June 2018, when astronomers detected an immensely bright flash of blue light in a distant corner of the sky. The burst appeared out of nowhere and then faded away in a matter of days. It was so strange and unexpected that they nicknamed it the Cow. This event turned out to be part of a new class of cosmic explosions called luminous, fast blue optical transients. These blue flashbulbs are among the brightest light shows in the universe, erupting like the flash of a camera and then disappearing almost as quickly. Only a handful have ever been seen. Each one shines intensely in blue hues and reaches peak brightness in days before dimming, far faster than an ordinary supernova. One such flash, in 2023, was even found far out in intergalactic space, nowhere near any galaxy, as if a brilliant beacon flared up in the emptiness. What could cause such a burst of energy in the middle of nowhere? Astronomers still aren't sure. These transients don't fit neatly into any known category of stellar explosion. They're like cosmic fireflies, winking at us from the dark and challenging our understanding of how stars live and die. And it's not just visible light that brings these surprises. In recent years, scientists have also discovered mysterious bursts in the radio spectrum, invisible flickers that carry tremendous energy. They're called fast radio bursts, brief blips of radio waves that last only 1,000th of a second, yet pack as much energy into that instant as our sun releases in days. Most fast radio bursts pop up at random and then vanish, never to repeat, which makes them hard to study. A few rare ones do repeat, firing off multiple bursts, but even those follow no pattern we can predict. Thousands of these radio flashes occur across the sky each day, coming from far beyond our Milky Way, and each one arrives without warning or explanation. For a long time, people wondered if they might even be signals from extraterrestrial civilizations, because of how odd they seemed. Now, we suspect many fast radio bursts might be caused by extreme cosmic objects like magnetars, neutron stars with ultra-strong magnetic fields, or colliding stars. But it remains a puzzle why some repeat and others don't. With every new burst detected, astronomers scramble to pinpoint its origin, hoping for clues. Yet so often, all we catch is the radio echo of a drama billions of light years away, a cryptic, solitary beep in the cosmic night. Stranger still, astronomers have found objects that emit bursts, not just once or in a quick series, but on a slow, regular cycle that defies what we thought was possible. In 2022, a team in Australia discovered a peculiar source that was turning on and off like a lighthouse. For about 2 minutes it would beam out radio waves and even X-rays, then go silent for over half an hour, then repeat, again and again. This happened every 44 minutes like clockwork. Nothing in our catalogues behaved quite like that. Normally, spinning neutron stars, pulsars, blink far faster, from milliseconds to seconds, not minutes. This object is unlike anything we have seen before, one astronomer said of the discovery. At first they thought it could be an exotic type of collapsed star, perhaps a highly magnetized white dwarf, or a magnetar slowly rotating. But even those ideas don't fully explain how it can produce such long, regular pulses. It's a mystery that challenges our understanding of stellar physics. Objects like this teach us that nature's cosmic lighthouse can have rhythms we never anticipated. In the quiet dark of space, something unknown is ticking, on a schedule that leaves scientists both baffled and intrigued. Not all celestial mysteries announce themselves with a flash or a signal. Some are revealed by a sudden absence, a light that should be there but isn't. Stars, especially massive ones, usually live for millions of years, and when they die, they go out with a bang, exploding as supernovae that shine brightly for months. That's the expectation, at least. So imagine the surprise of astronomers who noticed that a particularly large and unstable star they had been observing simply vanished. This star, located in a distant dwarf galaxy, was about 2.5 million times brighter than the Sun and had shown signs of being near the end of its life. Researchers pointed one of the world's biggest telescopes at its galaxy in 2019, expecting to see clues of a recent supernova. Instead, they found nothing. The distinctive light fingerprints of that star were just gone. It's as if the star had quietly winked out of existence. One possibility is that it underwent a failed supernova, collapsing directly into a black hole without exploding. If true, it would be the first time we've ever caught a star dying in absolute silence, without the farewell flare of a supernova. We may have detected one of the most massive stars of the local universe going gently into the night, one scientist said, evoking the poetic truth of that moment. It turns out this wasn't just an isolated case. When astronomers began comparing old sky images to modern surveys, they catalogued about 100 stars that appear to have vanished over the past century. These weren't stars that drifted behind dust or clouds. They seemed genuinely gone. Normally, stars might dim or brighten, or eventually explode, but simply vanishing is not something we expect. One research project, fittingly named the Vanishing and Appearing Sources During a Century of Observations, VASCO, is devoted to tracking these cases. So far, they have more than a few intriguing candidates. Stars here one decade and missing the next, with no supernova remains to show for it. What could cause this? The leading theory is again the idea of a failed supernova, a star so massive and exhausted that its core collapses under its own weight into a black hole, gobbling the star from the inside out. In such a scenario, There might be a brief flash of light or a weak belch of particles, but nothing like a typical supernova. An astronomer mused that if you were watching such a star at just the right moment, it might be like watching a star suddenly extinguish and disappear from the heavens. One instant it shines, and the next it's gone. It's a haunting thought. These silent disappearances remind us that even the life cycles of stars, which we thought we understood, still hold surprises. Somewhere in the universe, a giant sun can die with barely a whisper, and only careful eyes will notice its light has left us. While some stars slip quietly into darkness, others broadcast their demise in the most dramatic way imaginable, in blasts of gamma rays, the highest energy form of light. Gamma ray bursts, or GRBS, are like cosmic beacons of destruction, intense flashes of gamma radiation that can outshine entire galaxies for a few seconds. They were first detected by satellites in the 1960s and baffled scientists because these bursts seemed to come from random directions in space with no warning. Over time, we learned that the shortest GRBs, lasting less than 2 seconds, often come from colliding neutron stars, and the longer ones, lasting up to 10 seconds, often come from colliding black holes to a minute or more, are likely the death cries of massive stars collapsing into black holes. In essence, a gamma-ray burst is the universe's alarm bell for some catastrophic event. For a brief moment, a single burst can release more energy than our sun will in its entire 10 billion year lifetime. They are as extreme as physics gets. And yet, even here, the cosmos finds ways to surprise us. In October 2022, astronomers witnessed the brightest gamma-ray burst ever recorded. They nicknamed it the BOAT for brightest of all time. It was so intense that even at billions of light years away, detectors on multiple spacecraft were swamped by the signal. Events like that remind us that somewhere, a star met a violent end, sending a ferocious shout across the universe. But the real curveball came a few years later. In 2025, an even stranger gamma-ray phenomenon was observed. This wasn't a quick flash at all, but a prolonged event. A gamma-ray burst that lasted nearly an entire day and flashed repeatedly. For 24 hours, our instruments kept picking up burst after burst from the same patch of sky. Such behavior had never been seen in over 50 years of observing GRBS. Normally, a gamma-ray burst is a one-time event. A star can only collapse once, or 2 neutron stars can only merge once. Yet here was something that defied that rule. Initially, some suspected the source could be in our own galaxy, because nothing extragalactic should be so bright for so long. But when telescopes zeroed in, they found it was indeed coming from a galaxy billions of light years away. The usual explanations fell short. If it was a star collapsing, how could it sputter on and off for hours? If it was a black hole tearing a star apart, what kind of scenario would allow the energy to be released in stages like that? To this day, the cause of this peculiar, long-lasting gamma outburst remains unsolved. It's a vivid reminder that when we think we have nature figured out, nature finds a way to say, not quite. The universe's most energetic explosions still hold enigmas. And somewhere out there, something happened that we have never seen before, leaving us to puzzle over the clues. Sometimes, the strangest phenomena come from objects we thought were well understood. Take pulsars, the spinning neutron stars that send out beams of radiation like cosmic lighthouses. When pulsars were first discovered in 1967, their pulses were so regular that the discoverers half-jokingly nicknamed the first detection LGM1 for little green men, because it felt almost too orderly to be natural. It wasn't aliens, of course, but rather a rapidly rotating stellar remnant. Pulsars can spin anywhere from thousands of revolutions per minute to once every few seconds, and each time their beam sweeps past Earth, we detect a pulse of radio waves or light. They are some of the most reliable clocks in the universe. And yet, even these predictable beacons can act up in ways that mystify astronomers. Every now and again, a pulsar will suddenly and unexpectedly change its tempo. It might speed up slightly, a phenomenon known as a glitch, and then over days or weeks, gradually slow back down to its usual rhythm. These glitches are thought to be caused by starquakes or other internal upheavals in the ultra-dense matter of the neutron star's crust. They're like the neutron star equivalent of a hiccup or a tectonic shift, a brief jolt that momentarily alters the star's rotation. Approximately 190 of the 2,700 known pulsars have been recorded glitching. Between them, over 500 such glitches have been documented. That makes them uncommon, but not unheard of. Meanwhile, other pulsars show the opposite behavior. They pause. A pulsar can be merrily pulsing along for years, then fall eerily silent, no beats at all for a while, and later resume as if nothing happened. Some pulsars switch off for a few days or weeks. Others have been known to go quiet for months. It's as though a cosmic metronome skips a few beats or stops, then picks up the tune again. To explain these oddities, scientists sometimes have to get creative. One intriguing hypothesis is that tiny, invisible particles, or clumps of exotic matter, might occasionally strike a pulsar and alter its spin. A recent idea proposes that hypothetical, strange nuggets of dark matter, essentially small chunks of quark matter, could collide with a neutron star and produce minute spin changes. These strangelets, if they exist, might provide the extra nudge to cause micro-glitches, or even those puzzling slowdowns, sometimes called anti-glitches. It's a highly speculative notion, since we haven't detected such particles directly. But it shows how far we're willing to stretch our imagination to account for the surprises pulsars throw at us. The reality is, even though we use pulsars as precise cosmic clocks for navigation or tests of gravity, we don't fully grasp all the mechanisms at work inside them. Their crusts and cores, made of matter in states we can't replicate on Earth, might be doing things we haven't yet conceived. So when a pulsar glitches or goes quiet, it's a subtle message from nature. There are layers of complexity in these remnants of stars that we're still peeling back. Even our trusty celestial lighthouses have their secret storms and calm spells, reminding us that nothing in the cosmos is truly simple or completely predictable. On larger scales, the motions of stars and even entire galaxies have posed profound mysteries. In the mid-20th century, astronomer Vera Rubin found that stars in the outer regions of spiral galaxies, including our Milky Way, were orbiting much faster than expected. Given the visible mass of the galaxy, those outer stars should have been flung away by their own speed. Something unseen was providing the extra gravity to hold them in their orbits. That something is what we now call dark matter, an invisible substance making up the bulk of the mass in galaxies. Recognizing dark matter's presence was a revolutionary shift, born from the realization that our predictions failed unless we accepted an unseen influence. In our Milky Way, and indeed all galaxies we've checked, the stars' movements could not be explained by the glimmering matter alone. Thus, what began as an orbital discrepancy turned into evidence for dark matter enveloping galaxies like a hidden halo, binding the fast-flying stars with its gravity. But even after accounting for dark matter, not everything in the cosmic dance is understood. In recent years, astronomers noticed a curious trend on the grandest scales. Many galaxy clusters appeared to share a tiny but consistent motion in one direction, as if being pulled by something beyond the observable universe. They termed this the dark flow. By studying the slight distortions in the cosmic microwave background, the faint afterglow of the Big Bang, caused by clusters moving through it, scientists found an anomalous motion. Hundreds of distant clusters seem to be drifting toward a particular patch of sky, a motion independent of the universe's overall expansion. What could be tugging on them? One suggestion is that massive structures outside our observable cosmos, perhaps huge conglomerations of matter that we cannot see because they lie beyond the horizon of our visibility, are exerting a gravitational pull. This idea is mind-bending. It implies our known universe might be influenced by a greater unseen multiverse of sorts. Not everyone agrees on this dark flow's reality. It's a delicate measurement, and later data from other satellites have debated it. But if it's real, it means the distribution of matter we can see isn't the whole story. The cluster's coherent motion hints at a hidden landscape of matter and gravity, extending into the unobservable. It's like noticing that the gentle currents at a shoreline all seem to recede in one direction, suggesting a big ship passed by offshore, just out of sight. Whether or not dark flow is confirmed, the takeaway is humbling. Even at scales of billions of light years, we might be missing key pieces of the puzzle. The universe may have flows and currents, guided by forces and structures that we haven't mapped, reminding us that the cosmos extends far beyond what our eyes or telescopes can reach. Meanwhile, closer to home, we find anomalies in the paths of planets and stars that suggest invisible companions at play. One of the most intriguing questions in our own solar system is whether a large, unseen planet lurks far beyond Pluto. Astronomers studying the distant Kuiper belt, a realm of icy bodies on the solar system's outskirts, noticed that some of these objects have clustered orbits. Their elliptical paths are oddly aligned, as if shaped by the gravitational influence of something big out there. This led to the Planet 9 hypothesis. The idea is that an unseen planet, perhaps 5 to 10 times Earth's mass, orbits the Sun on a far-flung, elongated path, taking maybe 15,000 years to complete one revolution. Such a planet, if it exists, would be so distant that it reflects very little sunlight toward us and moves very slowly across the sky, which is why it hasn't been spotted yet. But its gravitational signature might explain why several distant dwarf planets all swing around the Sun in the same direction, with orbits tilted similarly and clustered in space. The search for this potential Planet 9 is ongoing. It's a modern twist in the tale of discovery, reminiscent of how Neptune was found in the 19th century via its pull on Uranus. But now we hunt with digital sky surveys and powerful telescopes. If and when it's found, it will be a triumph of inference. We'll have traced the unseen by its whispers in the orbital motions of known objects. Invisible masses aren't confined to the edges of the solar system. They can be hiding in plain sight among the stars. In 2022, astronomers unveiled the closest known black hole to Earth, and they found it not by seeing the black hole itself, but by observing the peculiar dance of a star. This star, which is only about 1,600 light-years away, was observed to wobble in a way that suggested it was orbiting something heavy, unseen, and compact. By carefully measuring the star's motion, scientists concluded it's bound to a black hole roughly 10 times the Sun's mass. The black hole itself is completely dark. It's not actively devouring matter, so it emits no X-rays or other telltale signals. It's essentially a silent gravitational ghost. The only evidence of its existence was the influence it exerted on its companion star, causing the star to move as if tugged by an invisible hand. This system, known as Gaia BH1, likely isn't unique. Our galaxy could be teeming with hidden two-body dances, stars quietly orbiting black holes or other compact objects like neutron stars, where we only realize the partner is there when our measurements become precise enough. There's also the possibility of rogue black holes, ones that carry no companions, drifting through the galaxy unseen, except when they occasionally magnify the light of background stars via gravitational lensing. We have tentative evidence for a couple of those as well. All these findings underscore that the darkness between the stars isn't empty. It's populated with things that sometimes make their presence known only indirectly. A wobble here, an odd orbit there. These are the clues. Every unusual path in the heavens hints at some hidden mass. It's a bit like detecting a fragrance in a still room. You know something unseen is nearby because of its subtle effect. The more we look, the more we realize that many celestial orbits aren't anomalous at all once you account for an unseen companion. It's just that the companion itself often challenges us to find it, forcing us to sharpen our senses and broaden our definition of what exists, even if we can't see it. As we scan the sky for hidden companions and listen for faint signals, we are also confronted with an eerie quiet. For all the billions of star systems in our Milky Way, we have yet to detect a single indisputable sign of another technological civilization. This odd silence forms the crux of the Fermi paradox. In a galaxy so vast and old, teeming with stars and planets, why hasn't anyone said hello? Our radio antennas have been tuned to the cosmos for decades, hoping to eavesdrop on the conversations of distant beings or catch a stray broadcast. We've listened across thousands of frequencies, pointed telescopes at promising star systems, and even sent out a few signals of our own. Yet, aside from the hum of natural cosmic phenomena, we've heard nothing that conclusively indicates intelligence out there. Statistically, it seems like we should have heard something by now, given the high odds for habitable planets and the potential for life to develop over cosmic timescales. But each passing year of quiet amplifies the question, are we really alone, or is everyone just really hard to reach? Some scientists speculate that intelligent life might be exceedingly rare, or very short-lived. Or perhaps it's out there, but communicating in ways we can't detect, like laser flashes, or neutrino beams, or something beyond our technology. Others wonder if civilizations tend to hide, deliberately maintaining radio silence in fear of predators, a concept known as the dark forest solution. Whatever the reason, the silence itself is telling. It forces us to reckon with the possibility that the miracle of talking, listening beings might be far more uncommon than the numbers might suggest. It also makes the night sky a bit poignant. All those stars, and perhaps no one, or very few, looking back. There have been moments, though, when the silence was pierced, if only briefly, and perhaps misleadingly. The most famous instance occurred on August 15th, 1977. That night, a radio telescope at Ohio State University, called the Big Ear, was surveying the sky when it recorded a sudden, strong, narrow-band radio signal. This signal was so anomalous, so unlike the background noise and natural sources, that when an astronomer reviewed the computer printout days later, he circled the reading and wrote "wow" beside it. Ever since, this has been known as the wow signal. It lasted just 72 seconds and was never heard again, despite many follow-up attempts. The signal's frequency was very close to a natural emission line of hydrogen, which some argued would be a logical universal hailing frequency for an intelligent beacon. Its intensity rose and fell in a way consistent with the telescope's scan. But because it didn't repeat, we could never confirm what it was. Over the years, hypotheses have ranged from a secret military transmission reflection to an overlooked comet, and more recently, one team suggested it might have been a natural emission from a hydrogen cloud energized by a distant object. Yet none of these explanations is certain, and the wow signal remains in the lore of cosmic mysteries as a tantalizing maybe. Aside from the wow signal, a few other interesting blips have popped up. In 2003, for instance, SETI researchers announced they had a handful of unexplained strong signals, but those too failed to repeat and were eventually chalked up to probable interference or just one-time flukes. In 2020, a directed SETI project detected a signal from the direction of Proxima Centauri that stirred excitement for a while, until further analysis revealed earthly origins. Each time, the pattern is similar: an intriguing hint, deep scrutiny, and then a mundane explanation, or an enduring ambiguity that keeps it out of the case-closed file. So here we are, ears open, and nothing definite to report. The quiet persists, a blank canvas on which we project our hopes and theories. It's possible that tomorrow we'll wake up to news of a clearly artificial signal pinging Earth from many light years away. But it's also possible that our solitude will continue for ages. In the meantime, the absence of evidence is itself a phenomenon to ponder. Maybe we are among the first to emerge in our galaxy, or the only ones right now, or destined to always just miss each other. The silence could be telling us something profound about life, intelligence, and the vast distances and times that separate islands of life in the cosmos. Until we break this cosmic radio silence, the void where alien voices should be is, in its own way, one of the loudest mysteries we have. Even the emptiness of space is not truly empty. Between the stars and galaxies, in the dark stretches of the cosmos, there is a faint glow, a kind of ghostly background illumination. You might think that if you point a telescope at a patch of sky with no stars or galaxies, you'd see pure black. But when the New Horizons spacecraft, far from Earth's light pollution, measured how dark the space between visible stars really is, it found an unexpected excess of light. This vanishingly faint glow is called the cosmic optical background, and it represents the combined light of all the stars, galaxies, and other luminous events in the universe, stretched and diffused over billions of years. What New Horizons revealed is that this background light is roughly twice as bright as the sum of known galaxies could account for. In other words, about half of that faint light has no identified source. It's as if countless dim objects, too faint to detect individually, or some other phenomenon, is adding a gentle sheen to the darkness. Astronomers have scratched their heads over this. Could there be far more dwarf galaxies or stray stars between galaxies than we realized, each contributing a drizzle of light? Or could the excess come from an exotic source, like the decay of hypothetical dark matter particles that only produce a soft glow? One researcher poetically described this puzzle as finding the universe is a little brighter than it should be. It's a bit like walking outside on a dark night and seeing a slight haze of light in the air, when by all rights it ought to be pitch black. Something in the universe, unaccounted by our catalogues, is lending a subtle luminescence to space. Until we pin down the cause, we have to admit that even the darkness between stars holds a surprise. A quiet glow that shouldn't be there, whispering that the inventory of the cosmos is incomplete. Another kind of mystery light comes not from steady glow, but from echoes of long-ago brilliance. In a canyon, you hear echoes because sound bounces off distant walls and reaches you delayed. In space, light can do something similar. Imagine a star exploding in a supernova, a catastrophic blaze of light. If that light travels outwards, Some of it might encounter big clouds of interstellar dust far from the explosion. The dust can scatter and reflect a portion of the light. We on Earth might miss the initial supernova. Maybe it was hidden behind other clouds or happened before we had telescopes. But years later, the reflected light finally arrives at our planet, giving us a second-hand show of an event already gone. These are called light echoes. They often appear as expanding rings or wispy illuminated clouds around where a supernova happened, and they can allow us to study the original event after the fact. A beautiful example occurred with a star named V838 Monocerotis, which had a sudden outburst in 2002. Over the months following, telescopes saw an expanding halo of light illumination moving outward through the surrounding space, essentially the light from the outburst lighting up successive shells of dust, like a widening ripple in a pond. It was gorgeous, and provided a three-dimensional sense of the dust around that star. Even more evocative is the story of Eta Carinae, a massive star in our own galaxy. Eta Carinae underwent a titanic eruption in the 1840s. Not a full supernova, but a supernova imposter event that made it one of the brightest stars in the sky for a time. Of course, in the 1840s, astronomy was done with the naked eye or small telescopes, and the details of that eruption were largely lost to history, aside from descriptions. But starting in the late 20th century and into the 2000s, astronomers looking at the region around Eta Carinae noticed patches of nebulosity that seemed to brighten and change over time in an unusual way. They eventually realized these were light echoes of that 19th century eruption, finally reaching Earth after bouncing off distant interstellar dust clouds. In effect, modern instruments got to capture a faint replay of the Eta Carinae outburst more than a century after it happened. By analyzing these echoes, scientists could infer properties of the eruption, its spectrum, its energy, as if they had a time machine bringing them information from the past. It's hard to overstate the almost eerie romance of that. We missed the big show, but the universe left us a recording in its vast archives of dust and space, which we could recover with patience and clever observation. Light echoes are a reminder that the universe has memory. The flash of a brilliant event doesn't always vanish without a trace. Sometimes it lives on, traveling through the cosmos, intersecting with dust clouds that act like cosmic mirrors. When we see an unexplained glow in a nebula, we have to wonder, is it something happening now, or the echo of something that happened long before, whose direct light has long since gone by? In the quiet and the dark, the dust can speak, carrying messages from events unseen. It's yet another way that the cosmos surprises us, not only with new phenomena, but with delayed revelations of known ones. A star's last breath, a century-old explosion, a transient burst. These can all leave an imprint that resurfaces later, as if the universe itself refuses to let the memory of bright things die out completely. From transient flickers to vanishing stars, from bizarre explosions to silent skies and ghostly echoes, we've journeyed through a cosmos that is far more mysterious and whimsical than our textbooks once suggested. Each enigma we encountered, a burst that shouldn't exist, a star that isn't where it ought to be, a silence when we expected noise, or a faint glow with no obvious source, is a reminder that the story of the universe is still unfolding. We find ourselves humbled by how much we don't know. And yet, there is a gentle excitement in that realization. The not knowing isn't a void to be feared. It's more like a dark forest path lit by fireflies, inviting us forward. In a way, These cosmic riddles are invitations. They call out to the curious part of us, saying, "Come look, there's something here you haven't seen before." They spark the imagination, encouraging us to dream up explanations and then devise ways to test them. Often, in trying to solve one mystery, we stumble upon others. We went looking for alien signals and discovered new natural radio phenomena. We hunted for hidden planets and found black holes quietly lurking. We examined supernova remnants and uncovered light echoes painting the sky. Each question opens a door to more questions. This can be seen not as a sign of failure, but as the very essence of science and exploration. The unknown is not empty, it's full of potential wonders. And so, under that moonless sky, with the band of the Milky Way above, we remain both awed and comforted by the mysteries around us. They remind us that we are young explorers in a vast, ancient universe. There are chapters and chapters of this grand story still to read. Perhaps tomorrow, a new flicker in the sky will draw our attention and start the next investigation. Perhaps with the next generation of telescopes, we'll finally get answers to some of these puzzles, or uncover deeper puzzles we can't yet fathom. The important thing is that the journey continues. The allure of the unknown keeps us moving forward, with a sense of wonder and humility. In the end, perhaps the greatest mystery is what lies ahead, just beyond the edges of our understanding. We pause here for a moment, not with a feeling of finality, but with anticipation. The cosmos is full of riddles, and each one we solve only deepens our appreciation for those that remain unsolved. The night sky still whispers to us, with flickers and silences and echoes we have yet to comprehend. We will keep listening, keep watching, and keep dreaming. Gently, under the quiet, starry expanse, we prepare ourselves to continue the quest, drawn onward by the soft call of uncertainty into whatever cosmic wonders await us next. In the silent ocean of space, we drift inward toward the Milky Way's heart. The light around us grows sparse as dust and gas thicken, hiding what lies ahead. Yet faint clues slip through this veil, whispers in radio waves and flashes of X-rays, hinting at something extraordinary deep within. For ages, the galactic center remained a mystery, a hidden realm sending signals across the void. And the closer we drifted, the stronger those whispers grew, beckoning us onward to uncover the source of this cosmic mystery. For centuries, the core of our galaxy was a blank spot to our eyes and telescopes. Thick clouds of interstellar dust block the starlight from deep in the center, making it invisible in ordinary light. Early astronomers saw the constellation Sagittarius crouching low in the summer sky, and knew our galaxy's nucleus lay in that direction. But all they perceived was darkness. Whatever was happening at the heart of the Milky Way, it unfolded behind a dark curtain, hidden from view, until we found other ways to look. Unlike visible light, radio waves can slip through the cosmic dust. By tuning into these longer wavelengths, astronomers found a way to peer behind the veil. Years before we could ever see the center in visible light, we heard its faint voice. In the early days of radio astronomy, one of the first antennas tuned to the sky picked up a persistent hiss from the constellation Sagittarius toward our galactic core. It was unlike anything experienced on Earth, a steady signal coming from deep space at a specific location. Astronomers realized the static wasn't noise at all, but a message from the heart of the galaxy, the first hint that something powerful lurked unseen. As radio telescopes sharpened their gaze, they pinpointed the source of this murmur. In the direction of Sagittarius, a compact, bright region crackled with radio energy. It came to be known simply as Sagittarius A, the beacon at the centre. Within it, an even more intense point was found, a tiny spark of radio light later named Sagittarius A star, the mysterious heart of the heart. Decades later, new eyes in the sky revealed that the galactic centre also glows in X-rays. High above Earth's atmosphere, X-ray observatories peered through the dust and found a faint radiance spilling from the core. Invisible to human sight, this energetic glow hinted at seething hot gas and violent events. It was as if the hidden heart of the Milky Way was leaking high-energy secrets, adding further intrigue to the tale. Because X-rays from space are absorbed by Earth's atmosphere, only observatories in orbit could detect this radiance. And the closer we looked, the more crowded it appeared. When the Chandra X-ray Observatory took a deep portrait of the galactic centre, it revealed thousands of individual X-ray sources dotting the darkness like sparks. Scattered among them was a faint, diffuse glow, a background haze of high-energy X-rays permeating the region. It was as if we had uncovered a bustling cosmic city at midnight, lit not by street lamps, but by the deaths and fury of stars and stellar remnants all around the central void. From time to time, the galactic centre would surprise its observers. Astronomers recorded sudden flickers and bursts that defied easy explanation. Strange radio signals would flare up and fade away, each one a brief question mark against the cosmic background. Every unexpected pulse or flash was a reminder that, at the galaxy's core, we were dealing with forces and objects beyond ordinary experience. All these emissions, gentle radio whispers, piercing X-ray glimmers, and sudden outbursts, pointed to an unseen powerhouse at the centre. It was like hearing the heartbeat of a creature too far to glimpse. Yet to truly understand what lay in that darkness, scientists needed another clue. They began to track the movements of the stars themselves, hoping the stars could tell the story of the invisible force holding court at the galactic centre. At first, even finding these stars was a triumph of technology and patience. Peering through the obscuring dust with infrared cameras, astronomers had to sharpen their vision using ingenious techniques to counteract the blurring of Earth's atmosphere. Little by little, they identified bright stars crowding around the galactic centre, and then they began to notice something remarkable. These stars were on the move. By tracking their positions year after year, scientists drew their paths in the sky, eventually mapping full orbits that looped astonishingly fast around an empty point. In the dense star fields near the galactic centre, a handful of stars stood out by the way they moved. Over years of patient watching, astronomers saw these stars tracing rapid, tight orbits around an apparent emptiness in space. It was as if they were bewitched, slung around by an invisible whirlpool. One star in particular, later given the name S2, raced around the unseen centre in just 16 years. An eye blink on cosmic timescales. At its closest swing, S2 hurtles at a few % of the speed of light, faster than any planet or comet known, in a path that carries it astonishingly close to the mysterious mass at the core. These dizzying orbits were like nature's laboratory, revealing the presence of an immense gravitational force. By mapping their curves, scientists could weigh the invisible object pulling the strings. The result was staggering. There had to be a mass millions of times that of our Sun packed into a space no larger than our solar system. Nothing ordinary could be so compact and massive. It became clear that only a supermassive black hole could wield such influence, anchoring these stars in their mad dance. If we could watch this celestial ballet up close, the sight would be mesmerizing. Imagine floating above the galactic center, seeing stars hurtle along curved paths that loop around an invisible point. They swing in close, accelerating to incredible speeds, then slingshot out again into the wider galaxy, only to be pulled back for another orbit. In the darkness, you would see these stars moving in ways that defy ordinary experience, a gravitational dance choreographed by a force that cannot be seen, only felt. These close passes also allowed scientists to test Einstein's theory of gravity in this extreme environment. As S2 swung by the central mass at its breakneck speed, the black hole's intense gravity stretched the star's light to slightly longer, redder wavelengths. This gravitational redshift was measured exactly as general relativity predicted, a subtle confirmation that even here, in the strongest fields our galaxy offers, Einstein's century-old ideas hold true. It was breathtaking to see such abstract physics come alive in the motion of a distant star. Even more perplexing was the nature of some of these stars. They burned young and hot, the kind of stars that normally form in tranquil nurseries, not in the tumult near a black hole. Their very existence so close to such a fearsome gravity well seemed to defy logic. It was a cosmic paradox. How could youthful stars arise or survive in a region that should tear star-making clouds apart before they can coalesce? Astronomers continue to puzzle over this paradox of youth, exploring ideas for how these stars found their way into the black hole's backyard. One idea is that these stars were born farther out in a star cluster that later migrated inward, the black hole capturing them in its deep gravitational well. Another hypothesis suggests they somehow formed in place from a disk of gas that briefly settled around the black hole, spawning stars during a rare moment of calm. Yet neither explanation fully satisfies the observations. The presence of these bright, youthful stars so near the galactic center remains an intriguing mystery lingering in the shadows of the core. Having confirmed the presence of this dark titan at the center, astronomers watched it with growing curiosity. Most of the time, the supermassive black hole sits quietly, barely a glimmer amid the surrounding stars. But every so often, it stirs. In the darkness where nothing should shine, a sudden flare will erupt, a brief flash of light from the black hole's vicinity that vanishes almost as quickly as it came. For such a tremendously massive object, the Milky Way's black hole is usually surprisingly quiet. Unlike the monstrous black holes in distant quasars that blaze like beacons, our central black hole is underfed and calm, emitting only a trickle of radiation most of the time. This made the sudden flares even more intriguing. Against a background of near darkness, these brief surges of light served as reminders that the black hole, though quiet, is still very much alive and active when it has something to devour. These flares are startling, as if a lighthouse beam flickered on deep inside a cave. They may last only minutes or hours, but in that time the region around the black hole can become dozens or even hundreds of times brighter. Telescopes on Earth and in orbit have caught these mysterious fireworks at infrared and X-ray wavelengths. Each flare likely means that something has fallen in or been torn apart, releasing a burst of energy as it vanishes beyond the point of no return. For a moment, imagine you were watching that black hole up close when one of these flares erupted. You might see nothing one instant, and then an eerie glimmer the next. A sudden glow illuminating surrounding gas and dust. It would be like a brief sunrise in the midnight of the galactic core, fading again before you could fully comprehend it. Such is the elusive nature of these flares, here and gone, leaving questions echoing in the darkness. In fact, minor flickers happen quite regularly. Sagittarius. A star has a handful of small outbursts every day that only sensitive instruments can pick up. Astronomers around the world keep watch, sometimes coordinating multiple telescopes to observe the black hole simultaneously, waiting to catch these transient glimmers. Each flicker and flare is a piece of a puzzle, potentially revealing how material swirls and feeds the black hole. By studying the timing and energy of the flares, scientists hope to learn how magnetic fields and matter dance in that extreme environment, just outside the point of no return. On one occasion, our galactic black hole produced a record-breaking X-ray flash, startling scientists with its intensity. For a brief moment, it blazed nearly 400 times, brighter than usual. Some speculated an unwary asteroid had wandered too close and been devoured. Others suggested tangled magnetic fields suddenly snapping and releasing their energy. The truth remains uncertain, but in that burst, we caught a glimpse of the black hole's wild hunger and power. In another instance, astronomers witnessed an unprecedented brightening in the infrared. The black hole's region glowing like an ember suddenly fanned. For a night, it was far more luminous than anyone had seen it before, hinting that perhaps it had just swallowed something substantial, or ignited a surge of hot gas. Such events remind us that this sleeping giant is not truly dormant. It's merely quiet until the next moment it feeds. These flares are fleeting signals, tantalizing and brief, of a beast that usually hides in shadow. Beyond the bursts of light and violence, the galactic center holds other strange marvels. When astronomers map the region in different wavelengths, they find structures that almost defy imagination. Among these are long, thread-like filaments seen in radio waves, stretching for dozens of light years across space. They hang eerily perpendicular to the plane of the galaxy, as if enormous magnetic wires were woven through the cosmic heart. Back in the 1980s, when astronomers first tuned high-powered radio telescopes toward the galactic center, they noticed something unexpected in their maps. Amid the chaotic radio glow of the core were thin, linear streaks of emission. These weren't the fuzzy clouds or round blobs one might expect from supernova remnants or star clusters. They were needle-like strands cutting through space. It was the first hint of the enormous filaments, structures that would puzzle scientists for decades to come. These filaments emit radio energy, which means they are filled with fast-moving electrons spiraling along magnetic fields. What created them remains a puzzle. Some filaments stand alone, solitary strands tens of trillions of miles long. Others appear in parallel bundles, almost like strings on a celestial harp, humming with energy. What makes them especially compelling is their order amidst chaos. In a region where gravity and turbulence reign, these filaments often stand remarkably straight and evenly spaced. Some run for dozens of light years, almost perfectly parallel to one another, like rungs on a cosmic ladder. It's as if giant magnetic field lines have been frozen in place and illuminated by cosmic electrons, creating a heavenly web in the heart of the galaxy. And just when scientists thought they had catalogued these structures, more appeared. New observations unveiled another set of filaments, shorter and oriented differently, some lying more horizontally, almost like spokes radiating toward the center. These unexpected newcomers hint that multiple processes might be at work, perhaps shockwaves from long-ago explosions, or past jets from the black hole arranging magnetic fields into these filamentary shapes. Every new filament discovered adds a piece to the puzzle, yet also deepens the mystery of how such structures came to be. Why do they exist, and why are they arranged so neatly? Some scientists suspect they could be remnants of an ancient eruption from the black hole, threads of energy left hanging long after a powerful blast. Others think they might be caused by cosmic particles shooting out from the center, tracing the otherwise invisible magnetic field as they go. With each new observation, nearly 1,000 filaments now revealed in recent years, the enigma only deepens, reminding us how much we still don't understand about our galaxy's core. While these silent filaments hung suspended in the galactic core, another cosmic drama was unfolding there. In the early 2000s, astronomers spotted a curious cloud of gas, later named G2, on a trajectory straight toward the black hole. It was a rare opportunity. Never before had we watched something plunge so closely past a supermassive black hole in real time. Excitement built as G2 drew nearer, like a small, delicate comet wandering toward a cosmic furnace, its fate uncertain. Scientists around the world predicted fireworks. As G2 approached the black hole's domain, tidal forces would stretch and shred it. The gas, they believed, might spiral in and trigger a brilliant flare as it was swallowed. Telescopes large and small turned toward the galactic center, waiting for the black hole to put on a show. But nature had a different plan. When G2 finally swooped in closest to the black hole, the anticipated explosion of light was subtle at best. The cloud did stretch out, like taffy pulled by gravity's hand, but instead of being torn to bits and consumed in a blaze, it mostly survived the encounter. The black hole, it seemed, barely sipped from G2, leaving astronomers scratching their heads. Telescopes pointed at the galactic center recorded only a gentle uptick in light as G2 made its closest approach. Instead of a brilliant flare, there was merely a flicker, a sigh where a roar was expected. The cloud, though stretched and skewed by gravity, remained largely intact, slipping past the black hole and continuing on its orbital path. In the aftermath, astronomers realized G2 must have some internal gravity of its own, perhaps a hidden star, or even a small cluster at its core, allowing it to survive the tidal onslaught. Why did G2 live to tell the tale? One possibility was that G2 wasn't a simple cloud at all, but perhaps concealed a dense core, a star enveloped in gas, that held it together. Another idea was that the black hole was simply not as hungry at that moment, and much of G2's gas kept going, swinging around and continuing its journey. Whatever the case, this cosmic near-miss taught scientists a humbling lesson. Even our best predictions can be upended by the galaxy's whims. Curiously, G2 may not be unique. Other strange objects, dubbed G1, G3, and so on, have been spotted near the center, each appearing as a cloud in some ways, but moving like a star. They might be stars cloaked in gas, similar to G2, orbiting silently until they, too, swing near the black hole and get a taste of its disruptive power. These hybrid entities hint at an unexpected population of oddities lurking in the central swarm. Just as G2 defied expectations, there may be more surprises awaiting discovery in the innermost orbits around the black hole. While the G2 cloud was an observable interloper, many denizens of the galactic center remain entirely invisible to us. Around the black hole's domain, astronomers suspect a swarm of hidden objects drifting in the darkness. In this crowded central zone, countless stars and remnants may be circling unseen, betrayed only by their gravitational pull or occasional flickers of X-rays. It's like a secret city around the black hole, a city of ghostly inhabitants that we only know are there by the subtle influence they exert. One likely constituent of this hidden population is black holes, smaller cousins of the giant at the center. Over billions of years, many massive stars in the galaxy live and die. They leave behind black holes and neutron stars that gradually sink toward the center under gravity's pull. Theory suggests thousands of these dark remnants could be gathered in the inner few light years around Sagittarius, a star, like a quiet swarm of embers orbiting a bonfire. In fact, X-ray observations have revealed a handful of such black holes in close proximity, detected as faint X-ray sources where they siphon gas from companion stars. This discovery of a dozen or so stellar black holes near the core hints that the predicted swarm is really there, perhaps thousands of unseen black holes lurking in the central dark. They themselves are nearly impossible to detect directly unless actively feeding. Only when one occasionally interacts with a star or cloud of gas does it produce a faint X-ray flare in the darkness, betraying its presence. Besides black holes, there could be entire clusters of dim stars or stellar remnants huddled near the core. Some evidence comes from the way stars move. Subtle deviations hint that more mass is present than what we visibly account for. A dense concentration of old, faint stars might be lurking, or perhaps clumps of dark matter, exotic particles that feel gravity but emit no light, adding their pull to the mix. For now, these masses remain hypothetical phantoms. We infer their possible presence from clues, but they slip through our surveys unseen. In fact, another mystery is not about what we detect, but what we don't. Galactic models predict a crowd of old, bloated red giant stars should have collected over time near the core. Yet when we look for these elderly stars, we find far fewer than expected. It's as though some process has pruned the population of old giants at the center. Either the black hole's gravity and past activity stripped them of their outer layers, or perhaps repeated supernova explosions cleared them out. This missing old stars problem is a clue that the environment at the center is harsher and more dynamic than we realized, and it hints that many stars we thought should be there have either been destroyed or dimmed below detection. For all we know, those missing giants might now lurk as dark remnants, dense neutron stars, or small black holes, blending into the unseen crowd at the center. Intriguingly, one such phantom may already have shown itself. A compact object, a few light years from the center, has been suggested as a possible intermediate mass black hole, far smaller than Sagittarius. A star, yet much larger than a typical star. If confirmed, it would mean even black holes can be pulled into the central congregation, merging over time to form a still mightier beast. Whether or not this particular case is real, the idea underscores how many hidden members might roam the central darkness, waiting to be discovered. At the very center of all these phenomena lies the ultimate mystery, a massive presence that we cannot actually see. Everything we've observed, from the whirling stars to the flashing flares, revolves around this one thing. It is Sagittarius, a star, the Milky Way's central black hole, and it behaves as a paradox, a tremendous mass occupying a tiny space, yet appearing to us as a void. In fact, the region from which no light escapes, the black hole's event horizon, is only about as wide as Mercury's orbit around the Sun, a minuscule realm to contain 4 million suns worth of mass. By its very nature, it emits no light of its own, a darkness even amidst the glow of surrounding stars. What does it mean to have a void at the galaxy's heart? A black hole is not a hole in the conventional sense, but a region where matter has been packed so densely that its gravity will not let anything escape, not even light. In a way, it's an object turned inside out. Everything that falls in is trapped beyond that one-way boundary. An object drawn too close will be pulled in. To a distant observer, it would appear to slow and dim as it nears that boundary, never quite seeming to vanish completely. Inside that boundary, all our understanding falters. Space and time themselves are warped to extremes, and the very fate of whatever crosses that threshold is concealed from us. For years, some wondered if there could be anything else at the center, perhaps a cluster of dark objects crowded together, or some exotic massive object, because a black hole, by definition, cannot be directly seen. But the behavior of the stars left little doubt. Whatever sits there has no surface, no ordinary boundaries. And in recent times, even technology has given us a peek at the silhouette of this abyss. A global network of radio telescopes, acting together as a planet-sized eye, captured an image of Sagittarius, a star. Not the black hole itself, but a glowing ring of hot gas orbiting a dark shadow, the telltale imprint of the hidden giant. That fuzzy ring of light and central shadow offered visual proof of the monster's existence, a sight that once lived only in theory, now made real. Yet, even with this image, and all our measurements, the true nature of what lies at the very core remains elusive. What is inside a black hole? Our theories speak of a singularity, an infinitely dense point where the mass of 4 million suns is compressed. But infinities are signs that our understanding breaks down. Some scientists speculate about exotic states of matter or hidden dimensions. But the reality is that beyond that horizon, we simply do not know what exists. It is a reminder that even at the center of our home galaxy, there are realms our knowledge cannot yet touch. Though our galaxy's heart is relatively calm today, it carries echoes of a wilder past. Just as a volcano might lie dormant while surrounding land bears the marks of its ancient eruptions, the Milky Way has scars and afterglows, betraying that the center once burst into fury. Around a decade ago, astronomers using space telescopes discovered giant bubbles of high-energy radiation billowing out from the galactic center, extending far above and below the Milky Way's disk. These enormous structures, invisible to our eyes but glowing in gamma rays, are like two lobes or chimneys, each stretching tens of thousands of light-years into space. These so-called Fermi bubbles are evidence of an immense release of energy from the galactic center millions of years ago. Their sheer size is staggering. Nothing short of a colossal eruption could have inflated them. Perhaps long before humans walked the Earth, our galaxy's core blazed as an active galactic nucleus, spewing out radiation and winds that carved these bubbles into the surrounding halo. Even now, they glow faintly in high-energy light, a fading afterimage of that ancient outburst. Intriguingly, scientists have also spotted column-like structures of X-ray and radio emission stretching upward from the galactic center, as if marking the route of those ancient outflows. These features, nicknamed cosmic chimneys, may have funneled energy from the central eruption into the giant bubbles we see today. They reinforce the idea that long ago our galaxy's core was blasting material outward, drilling into the halo with powerful jets or winds, while today the chimneys merely glow with residual heat and particles. They stand as monumental evidence of a period when the Milky Way's heart was far more tempestuous. The bubbles are not the only echoes of bygone violence. Closer to the center, astronomers have found that certain dense gas clouds are strangely glowing with X-rays, illuminated not by their own light, but by a flash that came and went in the past. These are like faint echoes in a canyon, except the canyon is the cosmos, and the original shout was a sudden blast from Sagittarius, a star centuries ago. By studying these X-ray reflections, scientists deduced that a few hundred years back, the black hole must have flared dramatically, perhaps millions of times brighter than today, briefly turning our galaxy's core into a quasar-like beacon. Though that flash has faded, its light echoes still wander the galactic center, bouncing off clouds and telling the story of a flare humans never saw. Even as we unearth evidence of past outbursts, we are confronted with phenomena in the present that remain unexplained. For instance, when we observe the center of the galaxy in certain high-energy wavelengths, we detect a faint but pervasive glow that simply should not be there, at least not according to what we expect from known sources. It's as though the darkness itself has a gentle luminescence in X-rays and gamma rays, a soft glow that no single star or remnant can fully account for. This mysterious background light has become one of the Milky Way's enduring riddles. For example, one puzzling glow comes in the form of a particular gamma ray signal pervading the central region. In the 1970s, high-altitude balloon experiments first detected an unusual emission line corresponding to about 511,000 electron volts coming from the direction of the galactic center. This radiation indicates a strange occurrence: electrons meeting their antimatter counterparts, positrons, and annihilating. This produces a very specific light, and yet we see far more of it near the galactic center than we can easily explain. What could be creating so many positrons in the bulge of our galaxy? It's a question that has lingered for decades, with theories ranging from undiscovered types of stellar explosions to the mysterious decay of dark matter particles. Another unexpected signal emerged in data from modern gamma-ray observatories. An excess of high-energy gamma rays at a few billion electron volts coming from the galactic center. When scientists modeled all the usual suspects, pulsars, supernova remnants, the frenetic activity of cosmic rays, they found these could not fully account for the observed glow. Something else was adding to the gamma-ray mix, forming a roundish cloud of energy. This discovery set off a wave of speculation that perhaps we were seeing the fingerprints of dark matter, the invisible substance that permeates the galaxy. If dark matter particles gather in the center and annihilate each other, they might produce just such a glow. However, the jury is still out. Many argue that a horde of millisecond pulsars, rapidly spinning stellar remnants, could also produce a similar signal if enough of them are packed into the bulge. Either answer would be profound. A dark matter origin would unveil an entirely new component of reality, while a pulsar origin would mean there are countless tiny spinning beacons hidden throughout the galactic center. As of now, the source of this gamma excess remains an open mystery, keeping the search for answers very much alive. Even lower in energy, the Milky Way's center long puzzled astronomers with a diffuse X-ray glow spread along the plane of the galaxy. For years, it was unclear why the central regions shone softly in X-rays everywhere, not just near obvious sources. Eventually, painstaking observations revealed that this so-called X-ray ridge was largely the sum of countless faint sources, myriad white dwarfs gobbling matter and other small-scale cosmic engines blending into a background haze. Still, a slight X-ray sheen remains, a reminder of how much starlight and star death commotion persist in the crowded galactic heart. Now we pause at the threshold of the galactic heart, with a sense of awe at what we have witnessed. The closer we looked, the more puzzles we found. We uncovered dramatic flares and invisible forces, saw evidence of cataclysms long ago, and lights with no clear source. Each mystery we explored deepens our appreciation for the complexity of this cosmic engine at the center of our galaxy. It is humbling to realize how much of the Milky Way's core remains uncharted. We listened to its whispers and saw fleeting flashes, but vast questions linger in that darkness. As we drift slowly away from the central black hole's domain, we carry with us the wonder it inspired, a sense of how small we are beside these titanic energies, and how creative nature can be in its cosmic tapestry. The galactic heart has told us a few of its stories, and kept many more to itself. But those untold stories continue to inspire us to seek answers, to listen in patience, and to prepare for the next chapter of discovery. Yet, our journey is far from over. From this central realm of wonders, we are ready to widen our gaze once again. Beyond the core lie the spiral arms, the stellar clusters, the halo of dark matter, and distant nebula, regions that hold their own secrets and phenomena waiting to be uncovered. We step back now, letting our field of view expand from the heart to the grand expanse of the Milky Way. Gently, we prepare to leave the brilliant, enigmatic center behind and venture outward, carrying with us the questions born in this voyage to the heart, as we continue to explore the riddles of the Milky Way. Far beyond the reach of our eyes, an enormous, invisible presence envelops our galaxy. It is as if the Milky Way drifts through a vast cosmic haze, a halo of matter that neither emits nor reflects light. This mysterious substance is known as dark matter, and though we cannot see it, we feel its gravitational pull. Every star, including our own sun, moves under its influence, a gentle but persistent tug from an unseen mass that outweighs all the glowing stars and nebula we know. In the silent darkness between the stars, dark matter forms an immense scaffold, a hidden framework shaping the Milky Way's structure and guiding the motion of everything within it. Astronomers had long suspected that something unseen might lurk in the depths of space. As early as the 1930s, a few researchers noticed hints of missing mass in the universe. In our own galaxy, the Dutch astronomer Jan Oort observed the motions of nearby stars and found they were moving as if more mass was present in the Milky Way's disk than the visible stars could account for. Far beyond, in distant clusters of galaxies, Fritz Zwicky famously calculated that galaxies in those clusters were flying around too fast, as though held together by the gravity of some hidden matter. These early clues were tantalizing whispers that not all of the universe's mass shines. At the time, they were largely overlooked or met with skepticism. Yet the idea of unseen matter quietly persisted, waiting for more evidence. Decades later, in the late 20th century, that evidence arrived and forced scientists to confront the invisible head-on. Astronomers mapping the motions of stars and gas in galaxies discovered that galaxies were not behaving as expected. In galaxy after galaxy, including our own Milky Way, the stars far from the center were moving too quickly to be held in orbit by the gravity of only the visible matter. Instead of slowing down at the outskirts, as planets do in the solar system, these stars maintained high speeds. It was as if an unseen gravitational hand were keeping them in line. This revelation, the discovery of unexpectedly rapid rotation in the outer regions, transformed those early whispers of missing mass into a resounding declaration that a new form of matter must exist out there. The picture that emerged was that our Milky Way is surrounded and permeated by a vast halo of dark matter. Picture the galaxy's bright disk of stars, gas, and dust, and then imagine a much larger, roughly spherical cloud enveloping it, completely transparent, yet enormously massive. The stars and nebulae we see are like a thin frosting on a cake, while the bulk of the cake is this invisible material extending far beyond the visible edges. By current estimates, over 80% of the Milky Way's mass lies in this halo of dark matter. It extends well beyond the outermost stars, perhaps several 100,000 light-years from the center, and thins out at the edges where our galaxy's influence fades into intergalactic space. Within this immense cocoon of darkness, our galaxy's stars orbit as if on a taut leash, bound by the gravity of an unseen realm. Though dark matter itself emits no light and cannot be observed directly, its presence is betrayed by its gravitational effects. It acts like a cosmic glue, binding our galaxy together. Without this invisible mass, the Milky Way would not hold its elegant spiral shape. The outer stars would drift away into space, and the spiral arms might never have formed or persisted. Indeed, certain features of our galaxy bear dark matter's fingerprints. For example, the Milky Way's disk has a slight warp in its outer regions, like a gently twisted ribbon. Some scientists suspect the dark matter halo's pull is responsible for this warp, especially if the halo is not perfectly symmetric. An invisible, off-kilter halo tugging on the disk could be the lingering result of an ancient collision that tilted the halo, and with it, the stars of our galaxy. We now face a profound mystery. We live within this dark matter veil, yet we still do not know what it is made of. It does not consist of the familiar atoms that make up stars, planets, and people. It passes through us and through the Earth undetected, interacting so feebly with normal matter that it might as well be a ghost. Physicists around the world have built sensitive detectors deep underground, hoping for a rare glimpse of a dark matter particle colliding with ordinary atoms. But so far, these experiments have found nothing definitive. Many theories attempt to explain the dark matter. Perhaps it is composed of exotic subatomic particles, relics of the Big Bang, that swarm through the galaxy like an invisible wind. Some scientists have named hypothetical candidates like WIMPs, weakly interacting massive particles, or axions, ghost-like particles that could fill the cosmos. Others have wondered if dark matter might not be particles at all, but rather a hidden population of objects, black holes, burnt-out stars, or other massive bodies that give off little to no light. For a while, there was hope that dark matter could be made of such astrophysical machos, massive compact halo objects, and astronomers designed studies to search for them. Those searches did find a few dim objects, and perhaps even isolated black holes drifting in space, but not nearly enough to account for the vast mass that dark matter must supply. Thus, the true identity of dark matter remains elusive. We know it is there in enormous quantities, yet it is still one of the greatest unsolved puzzles in science. In the quiet cosmic night, one can almost sense the presence of this vast, unseen mass. Imagine floating at the galaxy's edge, where the stars thin out and the darkness deepens, feeling a faint gravitational embrace from something you cannot see. The notion is both eerie and beautiful. Our Milky Way drifts through the universe enshrouded in this dark halo, like a ship moving through invisible waters. This hidden mass has shaped our galaxy's past, holds it together in the present, and will influence its future destiny among the stars. We continue our journey through the Milky Way's mysteries, carrying the awareness of this dark companion, a silent partner in the cosmic dance, unseen but ever present, its nature still veiled in shadow. One of the clearest signs of the Milky Way's hidden mass lies in the way it spins. For a long time, scientists assumed that the farther a star is from the galactic center, the more slowly it should orbit. This is the pattern we see in our solar system. The outer planets, like Jupiter and Neptune, move more leisurely around the Sun than the inner planets, like Earth or Mercury. By that logic, the stars at the fringes of our galaxy should drift along at a gentle pace, held only weakly by the distant pull of the galactic core. But when astronomers actually measured the speeds of stars and gas in the Milky Way, they were astonished to find a different story. Starting in the mid-20th century and growing clearer by the 1970s, observations showed that stars far out in the galaxy's disk were orbiting just as fast as stars much closer to the center. Instead of slowing down in the outer reaches, the stars kept up a brisk rotation speed, as if an unseen force were keeping them in step. This phenomenon came to be known as the flat rotation curve. The orbital speed stays nearly constant with distance, defying the drop-off one would expect. Our own Milky Way, studied through the motions of hydrogen gas in its outskirts, revealed this same perplexing pattern. It was as though the galaxy refused to thin out at the edges. Something unseen was providing extra gravity, holding the outer stars in their swift orbits. This unexpected behavior presented a profound puzzle. According to the laws of gravity, the only way those outer stars could move so fast and not escape the galaxy would be if far more mass were present than we can see. Even summing up all the stars, gas, and dust in the Milky Way, it wasn't enough to gravitationally tether those fast-moving outer stars. Without additional mass, the outer galaxy should fly apart, or at least rotate far more slowly. The fact that it doesn't means there must be a vast amount of invisible matter providing gravitational glue. This realization hit the scientific community with deep implications. Either our understanding of gravity on these scales was incomplete, or there existed an enormous amount of unseen matter in and around the galaxy. For most scientists, the simplest explanation for this anomaly was an invisible mass permeating the galaxy, what we now call dark matter. Flat rotation curves, observed by astronomer Vera Rubin and others, became one of the strongest pieces of evidence that dark matter is real. In the Milky Way, the effect is just as striking. The Sun, roughly 2/3 of the way out from the galactic center, orbits at around 200 kilometers per second, and stars even farther out move at nearly the same speed. This consistency in orbital velocity across vast distances is not what we'd expect from the visible mass alone. It's as if the Milky Way's bright disk is embedded in an enormous invisible cloud that extends well beyond our sight, and the cloud's gravity is pulling on everything within it. The discovery of flat rotation curves fundamentally changed our picture of the galaxy. It was a moment of revelation, a strong hint that the elegant swirl of the Milky Way is governed by more than meets the eye. For a time, some wondered if perhaps gravity itself behaved differently in the far reaches of galaxies, an intriguing idea we will revisit later. But the dark matter interpretation gained widespread acceptance because it could explain not only the rotation of our galaxy, but also a host of other cosmic observations. The realization sank in that for every star twinkling in the sky, there must be a mass of dark matter enveloping it, like a hidden companion. This notion was both unsettling and awe-inspiring, revealing that our understanding of the universe was incomplete. Even as we came to accept that dark matter underlies the Milky Way's rotation, the exact nature of this dark matter remained unknown. Still, the flat rotation curve stands as a clear, compelling message from the galaxy. There is more out there than the light we see. It beckons us to look for other signs of the unseen. And indeed, beyond the motions of stars, the universe offers another clue to invisible mass. Through the bending of light itself, a phenomenon known as gravitational lensing. High in the sky, a distant star suddenly brightens for a few weeks, then fades back to normal. There is no supernova, no explosion visible. Something invisible has passed in front of that star, acting like a cosmic magnifying glass. This phenomenon is known as gravitational lensing, an effect of Einstein's theory of gravity. In essence, mass bends the fabric of space, and light travelling through that distorted space will curve. We often see this on the grand scale, where entire galaxies or clusters of galaxies act as lenses, distorting the light of faraway quasars into arcs and rings. But here in our own Milky Way, lensing can happen on a much smaller scale too. Every now and then, a single unseen object drifts in front of a star and briefly focuses its light toward us. For a short time, that star appears brighter, even though the lensing object itself remains dark and hidden. Beginning in the 1990s, astronomers set up ambitious monitoring programs to catch these transient lensing events. They kept watch on millions of stars in the Milky Way's bulge and in nearby galaxies like the Magellanic Clouds, hoping to see the telltale brightening that signals a lensing event. When a star did brighten unexpectedly, careful analysis could reveal the presence and properties of the unseen lens. Was it a small star, a planet, or perhaps something more exotic, like a black hole? Each event was like a natural experiment, allowing scientists to weigh a dark object using only its gravity. These surveys, effectively a gravitational searchlight sweeping the galaxy, found dozens of such microlensing flashes over the years. The results were fascinating. Many of the microlensing events turned out to be caused by ordinary faint stars, or brown dwarfs, the kind of dim bodies that abound in our galaxy, but shine too weakly to be noticed individually. Yet a few events pointed to something even more mysterious. Objects too massive to be brown dwarfs, and yet entirely dark. Astronomers realized that these could be isolated black holes, or other heavy stellar remnants, drifting through the galaxy. Such objects, invisible to any telescope, would announce themselves only by the way their gravity bent the light of background stars. In one remarkable case, a background star in the Milky Way's spiral arm brightened and remained high for an unusually long time. Detailed follow-up observations suggested that the unseen lens was a black hole roughly 7 times the mass of our Sun. That black hole revealed itself purely by the way its gravity bent starlight passing by. This was a landmark discovery, the first likely sighting of a lone black hole wandering our galaxy, detected solely through its gravitational effect on a background star. Gravitational microlensing has also uncovered other hidden surprises, such as free-floating planets not bound to any star. These rogue planets, dark and cold, drift through the galaxy and can occasionally lens a star behind them. The lensing technique is so sensitive that it can detect even Earth-mass planets wandering in interstellar space. Such discoveries paint a picture of a galaxy filled not only with the stars we see, but also a multitude of drifting objects, from solitary planets to massive black holes, all virtually invisible until fate aligns them with a distant star's light. Crucially, these lensing surveys also taught us what dark matter is not. If the Milky Way's dark matter halo were made mostly of hidden star-like objects, the kind astronomers call MACHOS, we would have seen many more microlensing events than we did. The fact that we observed only a modest number of lensing flashes means the majority of the galaxy's missing mass is not locked up in dark stars or primordial black holes. Instead, it must be something more diffuse or fundamental, like the elusive particles scientists have hypothesized. These gravitational lensing experiments placed strict limits on how much dark matter could be composed of massive compact objects. And those limits suggest that ordinary dark objects make up only a small fraction of the Milky Way's dark matter. Still, the halo of our galaxy is far from fully understood. While microlensing failed to find an army of dark stars to explain dark matter, it did prove that our galaxy hosts a menagerie of unseen things: lone black holes, drifting planets, and other dim wanderers. Each microlensing flash is a reminder that darkness itself can be detected indirectly by the way it bends light. Without emitting a single photon, These hidden masses announce their presence through gravity alone. As we ponder what else might lurk unseen in the Milky Way, we turn our attention to the vast halo surrounding our galaxy, a realm where other mysteries, and perhaps other invisible structures, await discovery. The halo of the Milky Way is a vast, tenuous sphere of stars and dark matter surrounding the bright spiral disk. It extends far beyond the galaxy's visible boundaries, a mostly transparent realm dotted with ancient star clusters and the occasional small satellite galaxy. For a long time, this halo was thought to be relatively featureless, a sparse, round cloud of old stars. But as astronomers have peered deeper, they have discovered that the halo is anything but smooth. It is laced with enigmatic structures and patterns, the telltale marks of our galaxy's complex history. One striking discovery is that the halo contains streams and clumps of stars, as if left behind by long-lost companions. When a smaller galaxy ventures too close to the Milky Way, our galaxy's gravity can tear it apart, strewing its stars across the sky. In recent years, astronomers have identified several such stellar streams, faint bands of stars wrapping around the Milky Way. One of the most prominent examples comes from the Sagittarius dwarf galaxy, a small galaxy that has been gradually shredded over billions of years. Its stars now form a sprawling stream that loops around the Milky Way, a ghostly highway of stars in the halo. These star streams are like footprints of past mergers, providing direct evidence that the Milky Way grew by cannibalizing smaller systems. In addition to streams, the halo harbors other puzzling stellar structures. Observations have revealed, for instance, a gigantic, diffuse ring of stars encircling the Milky Way's outer disk. This ring, which lies tens of thousands of light-years beyond the Sun's orbit, was discovered by mapping stars in the far reaches of the disk. It might be the remnants of a dwarf galaxy that was swallowed and stretched into a ring-like form, or perhaps a ripple excited by an ancient collision. The very existence of this enormous, faint structure came as a surprise, hinting that our galaxy's outskirts are far more dynamic and layered than once assumed. Even the Milky Way's satellite galaxies present a mystery in their arrangement. The dozen or so known dwarf galaxies that orbit our own are not scattered randomly, as one might expect. Instead, many of them seem to lie roughly in the same plane, a flattened arrangement dubbed the satellite plane. What's more, in some studies, they appear to be moving in sync along this common plane. This is puzzling because our best cosmological models predict that satellites should be distributed more or less randomly around a galaxy. Scientists are debating whether this alignment is a cosmic coincidence or a sign of something we don't understand about how galaxies form. It could be the residue of a past group of galaxies that fell in together, or it might challenge aspects of the dark matter theory. For now, the planar grouping of our satellite galaxies remains an open question, a geometric oddity on a galactic scale. The halo is not only populated by stars, but also by sprawling clouds of gas and energetic phenomena. A colossal stream of hydrogen gas, known as the Magellanic Stream, stretches behind our galaxy's two largest satellite galaxies, the large and small Magellanic Clouds, like a long flowing tail. This stream arcs through the halo over hundreds of thousands of light years. It likely formed from gas torn out of the Magellanic Clouds by tidal forces as they orbit the Milky Way. But aspects of it, such as its unexpected length and mass, continue to intrigue researchers. Additionally, towering above and below the Milky Way's center are the so-called Fermi bubbles, two enormous lobes of high-energy gas and particles detected in gamma rays. Each bubble spans about 25,000 light-years. They appear as faint gamma-ray glows, billowing out perpendicular to the disk, as if some powerful eruption from the galactic center blew hot gas straight into the halo. Whether these bubbles were caused by an ancient outburst from the Milky Way's central black hole or a period of intense star formation is still under investigation. They are a vivid reminder that the halo, though seemingly quiet and dark, has been a stage for dramatic events. Every new discovery in the halo has deepened our understanding that the Milky Way is a galactic patchwork, stitched together from countless interactions and collisions. The halo preserves the fossils of those events, streams of stars, orphan clusters, rings, and clouds that tell the story of bygone galaxies and upheavals. Yet many questions remain. How many more faint streams and satellite galaxies await discovery in the darkness? Are the unusual alignments we see just statistical flukes, or do they point to new physics? As astronomers map the halo with ever greater precision, they are essentially reading the Milky Way's diary, deciphering chapters of violence and growth. While the halo's mysteries loom large, not all unexplained phenomena lie in that distant realm. Closer to the galaxy's heart, within the disk and spiral arms, other secrets persist. Even in the relatively crowded plain of the Milky Way, there may be invisible giants lurking, objects like black holes that roam among the stars unseen. Our journey now turns back inward, from the far-flung halo to the bustling disk, as we seek out evidence of these stealthy wanderers within our own galactic neighborhood. Within our galaxy, hidden among the stars, there may be countless black holes drifting silently through the darkness. When a massive star reaches the end of its life and collapses, it can leave behind a black hole, an object so dense that not even light can escape its grasp. Over the billions of years of the Milky Way's history, many giant stars have lived and died, and in their wake, they have likely seeded the galaxy with these invisible remnants. Unlike the supermassive black hole anchored at our galaxy's core, these smaller black holes are scattered throughout the Milky Way's disk and halo. Each is like a tiny gravitational pit moving through space, unseen, except for its influence on nearby matter. Astronomers estimate that the Milky Way could harbour millions of stellar mass black holes. Most of them wander quietly, not close enough to any star or gas cloud to draw in material and flare to life. A black hole on its own emits no light. It merges into the darkness around it. Only when a black hole feeds, for example, by pulling gas from a neighbouring star, does it become visible, often as a bright X-ray source. Indeed, several decades ago, astronomers began finding X-ray binaries, star systems where an ordinary star orbits an unseen companion that was eventually identified as a black hole siphoning matter. These rare luminous episodes told us black holes were out there. But what about the ones that have no companion to betray them? Until recently, those remained purely theoretical. New methods are now allowing us to detect these solitary, wandering black holes. One technique, as we have explored, is gravitational microlensing. When a black hole passes in front of a distant star, it can act as a lens and briefly magnify the star's light. Such events are extremely uncommon, but they provide a unique way to find a completely dark object. In fact, one of the microlensing events observed in our galaxy turned out to be caused by an invisible object around 7 solar masses, very likely an isolated black hole drifting through the galactic disk. This discovery was a first step in confirming that solitary black holes are not just theoretical. They really do roam the Milky Way. Another breakthrough has come from tracking the motions of stars with exquisite precision. The Gaia Space Observatory, for example, measures the positions and movements of billions of stars in our galaxy. Among these stars, a few show a telltale wobble, as if an invisible massive partner is tugging at them. Recently, astronomers announced the discovery of a sun-like star orbiting a dark companion roughly 10 times the Sun's mass, almost certainly a black hole. Unlike the X-ray binaries of the past, this black hole isn't actively feeding, so it remains invisible. But its gravity betrays its presence by pulling its stellar partner in a gentle dance. This finding demonstrated a powerful new way to hunt hidden black holes by using stellar motions as signposts for the invisible. What are the fates of these wandering black holes? In most cases, they will continue to drift endlessly around the galaxy. They pose little threat to us. Space is vast, and even with millions of black holes sprinkled through the Milky Way, the chance of one coming close to our solar system is extremely remote. Occasionally, a black hole might encounter a cloud of gas or stray too near a star and reveal itself through a burst of radiation. But otherwise, they are silent travelers. These objects are relics of earlier generations of stars, each one a kind of fossil roaming the galactic graveyard. The notion that immense, invisible masses are moving through our cosmic neighborhood underscores how incomplete our view of the galaxy remains. Even after accounting for black holes, both isolated and in binaries, they make up only a fraction of the elusive dark matter. To explain the rest of the Milky Way's missing mass, we must look to other solutions. And as we examine the galaxy's broader structure, another discrepancy comes into focus. According to theory, the Milky Way should have far more small satellite galaxies than we currently observe. This is the so-called missing satellites problem, another riddle of the Milky Way waiting to be unraveled. According to our best cosmological models, big galaxies like the Milky Way should be accompanied by swarms of smaller ones. In simulations of the universe, a large dark matter halo, like the one our galaxy sits in, ought to contain hundreds of lesser clumps, each potentially hosting a tiny galaxy. In other words, the Milky Way's family tree should be crowded with dwarf galaxies orbiting around it. These models predict far more satellites than the number of known dwarf galaxies we see today. For a long time, the Milky Way appeared to have only a sparse entourage. By the end of the 20th century, astronomers had identified just over a dozen dwarf satellite galaxies circling our galaxy. The brightest examples like the Large and Small Magellanic Clouds, and a handful of fainter ones, such as the Sagittarius, Draco, and Ursa Minor dwarfs. This was a surprisingly small number compared to theoretical expectations. The discrepancy became known as the missing satellites problem. It seemed as if many of the Milky Way's predicted companions were simply not there. In the early 21st century, deeper surveys began to reveal that we had been missing some of the Milky Way's shyer relatives. Sensitive telescopes and digital sky surveys, such as the Sloan Digital Sky Survey, started uncovering extremely faint dwarf galaxies that had eluded detection. These ultra-faint dwarfs are mere smudges of light containing only a few thousand stars, and they shine so weakly that they nearly blend into the background of the sky. Dozens of these tiny galaxies have been discovered in the past 2 decades. Their existence has alleviated the missing satellites problem somewhat. The census of Milky Way satellites has grown. But even with these additions, the number of observed dwarfs is still on the low side of theoretical predictions. Why might so many satellites be missing from view? One possibility is that they are there, but we just can't see them. The smallest dark matter clumps might not have ever formed many stars. Early in the Milky Way's history, intense starlight and supernova explosions could have blown away the gas from these tiny protogalaxies, stunting their growth. A dark matter halo without stars would be effectively invisible to us. There could be dozens or hundreds of dark satellites, essentially starless mini-galaxies, orbiting the Milky Way undetected. Another idea is that the theory itself needs adjusting. Perhaps dark matter isn't as cold, slow-moving as we think. Warm, dark matter particles, which move faster, would clump less on small scales, naturally producing fewer dwarf galaxies. This could reconcile the predictions with the observed count. Ongoing searches continue to look for faint satellites in our galactic neighborhood. The advent of powerful observatories like the Vera C. Rubin Observatory, with its legacy survey of space and time, promises to unveil even dimmer and more distant dwarf galaxies, if they exist. Each new discovery adds a piece to the puzzle, helping us understand the threshold at which a dark matter halo can form a galaxy of stars. In tandem, improved simulations of galaxy formation are incorporating more physics, such as the effect of cosmic rayonization and feedback from young stars, to refine their predictions of satellite numbers. The missing satellites problem reminds us that what we see is only part of what is there. It's possible that the Milky Way's halo is teeming with substructures that have little or no starlight. How could we find such invisible satellites? One intriguing method is to observe their gravitational influence on other objects. For example, if a dark satellite passes through a stream of stars, the remnants of a disrupted dwarf galaxy, it might disturb the stream's path, leaving telltale gaps or kinks. Astronomers have begun using the fine detail in stellar streams as a kind of radar for unseen masses. In this way, even a completely dark clump of matter could reveal itself by the ripple it creates in a stellar stream. Bit by bit, the Milky Way's retinue of satellites is coming into focus, and the gap between theory and observation has narrowed, though not yet closed. As we probe deeper into the halo for these elusive dwarfs, we are not only testing our understanding of dark matter, but also learning how galaxies like our own assembled over time. Ultimately, resolving the missing satellites puzzle will illuminate the interplay between the seen and unseen in our universe, and perhaps even point the way to new physics. As we continue our search for these ghostly galaxies, we cross paths with another clue in our galaxy's halo: the delicate streams of stars that wind around the Milky Way, relics of past galaxies and potential keys to detecting the unseen. Encircling our galaxy are a number of narrow, ghostly bands of stars, stellar streams that stretch across the sky. These streams are the remnants of galaxies or star clusters that ventured too close to the Milky Way and were pulled apart. As the Milky Way's gravity tugs on these smaller systems, their stars get strung out along their original orbits, forming elongated trails. To an observer, a stellar stream appears as a faint, linear grouping of stars, all moving in concert around the galactic center. They are like chalk marks left behind on a blackboard, outlining the paths of former companions that the Milky Way has torn to shreds. One of the most famous streams comes from the Sagittarius dwarf galaxy, which we discussed earlier. The Milky Way has been in the process of devouring this small galaxy for eons. As a result, a huge stream of its stars now wraps around our sky. The Sagittarius stream forms an almost complete ring around the Milky Way, with leading and trailing arms that pass over the galactic poles. It was one of the first clear pieces of evidence that our galaxy is actively cannibalizing its neighbors. Even today, the core of the Sagittarius dwarf galaxy continues to orbit and shed stars, adding to its lengthy stellar tail. The stream's stars, though now far from their original home, still move coherently together, whispering the story of the galaxy they once belonged to. Not all streams originate from destroyed dwarf galaxies. Some come from globular clusters, those dense spherical collections of ancient stars. When a globular cluster drifts into the Milky Way's tidal field, it too can start to lose stars. An example is the Palomar 5 cluster, which has been stretched into a thin stream of stars that arcs across the halo. This stream is extraordinarily narrow and gently curved, like a strand of cosmic silk. Its stars are all roughly the same age and composition, reflecting their common origin. Streams from globular clusters tend to be fainter and thinner than those from dwarf galaxies, but they are just as telling. They delineate the gravitational contours of the Milky Way with exquisite precision. Stellar streams are described as cold structures, not in temperature, but in dynamical terms. Being thin and coherent, they have very little random motion within them, hence cold, meaning the stars move almost in lockstep. This makes streams sensitive probes of the gravitational forces they encounter. If something disturbs a stream, say a massive clump of dark matter or an unseen object crossing its path, the stars will be perturbed in a noticeable way. In recent years, astronomers have found hints of such disturbances. One long stream, named GD1, has an unexpected gap and an odd kink in its stellar distribution. The best explanation for this feature is that something big collided with the stream, perhaps a dense dark matter subhalo that contains no stars, or a black hole wandering through the halo. It's a cosmic crime scene. The stream's once smooth path has been disrupted, and the evidence suggests an invisible culprit. The discovery of gaps and wiggles in stellar streams has raised exciting questions about the unseen mass in our galaxy's halo. These irregularities offer direct evidence that the Milky Way's halo is not a smooth continuum, but peppered with unseen mass. By studying such disturbances, astronomers can attempt to count and weigh the invisible dark matter subhalos that populate our galaxy. A key question is whether the frequency of stream perturbations matches what cold, dark matter theory predicts. So far, the evidence from streams is broadly supportive, but the sample remains small. Some scientists have speculated that a passing dwarf galaxy or an intermediate mass black hole could be responsible for certain stream anomalies. Every perturbation is a question mark, prompting us to ponder what unseen structure might have caused it, and sharpening our understanding of what lurks in the darkness. As delicate as they are, stellar streams have become one of the hottest tools for mapping the Milky Way's invisible mass. Ongoing surveys, including data from the Gaia mission, have revealed numerous streams crisscrossing the sky, and no doubt more await discovery in the furthest reaches of the halo. Each stream is a tangible record of a past encounter, a galactic memory made of stars. By decoding those memories, we learn not only about the Milky Way's history of mergers, but also about the distribution of dark matter that orchestrates those mergers. The cold streams pose hot questions. How clumpy is our galaxy's dark matter halo? Did smaller galaxies leave behind unseen debris that still drifts out there? The answers lie in patiently charting these stellar highways. Our exploration of stellar streams highlights how much of our galaxy's structure is only revealed through careful observation and inference. Not everything in the Milky Way announces itself with bright starlight. In fact, some structures remain hidden to optical telescopes altogether, only coming to light when observed in other wavelengths. It turns out that if we shift our gaze to the infrared, a whole new set of ghostly galactic features emerges from the darkness, waiting for us to discover. Much of our galaxy is concealed behind veils of interstellar dust when we look with ordinary eyes. This dust absorbs and scatters visible light, hiding the Milky Way's true structure from view. For decades, astronomers gazing toward the galactic center saw only darkness, punctuated by a few stars, a vast zone of avoidance where optical telescopes could reveal little. But by observing the sky in infrared light, which can penetrate dust, a new picture of the Milky Way has emerged. Infrared surveys have peeled back the obscuring clouds, unveiling features that were once only suspected or completely unknown. One of the remarkable structures brought to light by infrared observations is the Milky Way's central bar. Our galaxy is a barred spiral, but the existence and size of that bar were difficult to ascertain in visible light due to dust in the inner regions. In the 1990s, data from COBE's infrared camera first hinted strongly at a stellar bar running through the galactic center. Later, the Spitzer Space Telescope mapped millions of stars in the Milky Way's plane, confirming a bar tens of thousands of light-years long. This structure was invisible in optical surveys, but obvious in the infrared. Along with the bar, infrared imaging charted the inner spiral arms, revealing where stars and dust weave around the core in intricate detail. Infrared vision has also led to the discovery of entire clusters of stars that were invisible before. Near the galactic center, astronomers found several dense clusters by their infrared glow. These clusters are filled with young, massive stars cloaked in dust. No optical telescope could see them. Similarly, infrared surveys of the Milky Way's disk have unveiled numerous small star-forming regions and even new spiral arm segments that were hidden behind dust clouds. What looked like empty darkness in visible light often turns out to contain vast structures when viewed in the longer wavelengths of infrared. In a sense, the infrared has filled in gaps in our galactic map, populating the darkness with previously unseen stars and nebula. Perhaps the most evocative of the infrared revelations are the dark silhouettes and filaments, the ghostly shadows highlighting the galaxy's coldest, densest places. In mid-infrared images from space telescopes, a bright glow of warm dust permeates the Milky Way's plane. Against that glow lie patches of darkness, extremely dense molecular clouds that even infrared light cannot penetrate. These are the cradles of future stars, clouds so full of gas and dust that they have yet to form luminous suns of their own. Invisible in optical surveys, they announce themselves only by blocking the infrared background, appearing as elongated, wispy shadows, sometimes tens of light-years long. From the bulging center to the far-flung rim, the Milky Way in infrared is a very different sight, one alive with structures that were once hidden in darkness. We now see glowing star-forming nebulae, previously obscured, lighting up the infrared sky. We find cool, dusty rings and shells around evolved stars, and shockwaves, like the bow waves of speeding stars, visible only in the infrared. Each of these structures tells a story, of stars being born, of stars dying and shedding their shells into space, or of stellar winds ploughing through the interstellar medium. They add depth to the Milky Way's portrait, reminding us that our view of the universe depends profoundly on the wavelength of light we use. Even with these advances, the Milky Way keeps some secrets. Sometimes, the question isn't just about what we can't see, it's about whether we're interpreting what we do see correctly. As we unveil hidden matter and structure with tools like infrared telescopes, other puzzles make us question the very foundations of our understanding. Could it be that some phenomena attributed to invisible mass are hinting instead at a flaw in our theory of gravity? This is the provocative idea behind our next mystery. Before concluding our journey, we will explore the bold notion that the apparent gravity that isn't there might suggest a new chapter in physics, one that challenges the existence of dark matter itself. For decades, the solution to phenomena like flat rotation curves and hidden mass, has been to assume there is invisible matter, dark matter, providing the gravity that seems to be missing. But what if there is no missing matter at all? A bold alternative suggests that our theory of gravity itself might be incomplete. Perhaps the laws governing stars and galaxies are a bit different from those we learn from an apple falling on Earth, or planets orbiting the Sun. This idea sounds radical, but it springs from a simple question. If we cannot find gravity's source in unseen matter, could it be that gravity behaves in unexpected ways on cosmic scales? In the 1980s, a physicist named Mordechai Milgrom proposed a modified view of gravity. He noted that the discrepancy, stars moving too fast at the edges of galaxies, only became apparent when the acceleration due to gravity dropped below a tiny threshold. Milgrom suggested that at these very low accelerations, the usual Newtonian law of gravity might change. His hypothesis, called modified Newtonian dynamics, MOND, was formulated to make gravity a little stronger on galaxy scales than expected from visible matter alone. In a Mondian universe, no dark matter is needed to explain galaxy rotations. The laws of motion themselves do the job by giving a small boost to gravity in the regime of feeble accelerations. At first glance, MOND was a speculative exercise, and many scientists were skeptical. Yet, remarkably, this tweak to gravity does reproduce the rotation speeds of many spiral galaxies quite well. With a single additional parameter, MOND can generate flat rotation curves that match observations for numerous galaxies, from large spirals to small dwarfs. It was hard to ignore the elegance of this idea. Instead of inventing a whole new kind of invisible matter, change the rules of gravity slightly, and the need for dark matter in galaxies vanishes. Some proponents argue that this success is a hint that our understanding of gravity, based on Newton and Einstein, might not be the final story when it comes to galaxies. However, modifying gravity remains controversial, and MOND faces serious challenges. While it may handle galaxy rotations, it struggles to account for phenomena on larger scales. Galaxy clusters, or the universe's early history, still seem to require something like dark matter. The famous bullet cluster collision, for example, shows a separation between normal matter and gravitational mass that MOND alone can't easily explain. In response, proponents have extended MOND into more complex frameworks or devised new theories, such as adding extra fields to gravity to try to address these issues. So far, none of these alternatives has matched the dark matter model in its scope or acceptance, but the exploration continues. The debate between modifying gravity and invoking dark matter highlights a fundamental choice in explaining cosmic mysteries. There are two approaches: invoke unseen mass, dark matter, or alter the laws of gravity. Most astronomers still favor dark matter, largely because independent evidence, from gravitational lensing, galaxy formation simulations, and more, strongly supports the presence of unseen mass. Yet a small but tenacious group of researchers explores the alternate route, honing their gravity-based explanations. They point out, for example, that MOND naturally predicted certain relationships, like the observed tight correlation between a galaxy's rotation curve and its visible mass, that were later observed and form the empirical basis of an empirical acceleration relation. So far, no modified gravity theory has been able to explain all the phenomena dark matter can, and no detection of dark matter particles has yet confirmed their existence. We find ourselves in a cosmic detective story with two leading suspects, something we can't see or something we don't fully understand. It is possible that in the end, reality will involve a bit of both. Perhaps dark matter exists, but we also need to tweak our theories of gravity slightly. Or perhaps an entirely new theory will emerge that subsumes both ideas. For now, we remain unsure. And it's this uncertainty that is both frustrating and exciting. It reminds us that there are fundamental pieces of the universe still beyond our grasp. As we come to the end of this journey through the Milky Way's mysteries, the idea of modifying gravity serves as a humbling reminder. Even our most cherished physical laws are subject to revision in the light of new evidence. Whether the answer to the missing gravity lies in shadowy matter or new physics, the pursuit itself deepens our understanding. In the quiet of contemplation, under the dark night sky filled with stars, we can reflect on how far we've come and how much remains unknown. In that peaceful unknowing, we prepare to step back and simply marvel at the galaxy's wonders, even as the questions linger open. The Milky Way holds its secrets closely, but in seeking them, we have experienced the thrill of discovery and the humility of not knowing. We have journeyed through the invisible halo and along ghostly streams of stars, listened to whispers of dark matter, and entertained daring notions of new physics. Now, under the soft glow of billions of distant suns, we pause. In this quiet interlude, we allow the enormity of what we don't yet understand to simply exist without pressing for immediate answers. There is a serenity in acknowledging the unknown. The galaxy's unresolved mysteries, the unseen mass, the unexplained motions, the hidden structures, need not provoke frustration alone. They also inspire wonder. We find comfort in the fact that there is so much more to learn, that the cosmic story is far from fully written. In the grand scheme, our Milky Way is but one galaxy among billions, and yet here we are, striving to decode its riddles. Each question answered leads to new questions, and so the pursuit continues in an endless, enriching loop. As we linger in this moment of reflection, we can almost feel the gentle tug of the galaxy's gravity and the subtle presence of the dark matter halo enveloping us. The mysteries we explored do not diminish the beauty of the night sky. If anything, they enhance it. Every star we see, and even those we cannot, become symbols of curiosity. We remember that the darkness between the stars is not empty, but filled with possibilities. Unseen worlds, uncharted phenomena, undiscovered truths. Our voyage through these galactic enigmas has been both a scientific odyssey and a philosophical one. It reminds us that being comfortable with not having all the answers is part of the scientific spirit. In the silence of what we have yet to learn, there is a profound peace. We take this moment to breathe in the cosmic perspective, to recognize our place in a galaxy that is as mysterious as it is magnificent. From here, we will carry onward, curiosity undimmed. The pause ends, but the exploration does not. With renewed wonder, we prepare to rejoin the quest for understanding, ready to venture deeper into the unknown. The Milky Way's riddles remain, waiting quietly for us to return and unravel them, one by one, under the calm and watchful sky. In the silent darkness of space, not every star shines with a steady light. There are stars that flicker unpredictably, or swell and shrink as if unsettled by some hidden force. These variable enigmas have caught astronomers off guard with their baffling behavior. One moment they gleam brightly, and the next they fade or throb in intensity without a clear rhythm or cause. For a skywatcher, it's as if these stars are alive with restless energy, sending out cosmic Morse code that no one yet fully understands. Some stars vary in brightness in well-known ways, pulsating gently over weeks or months in a reliable cycle. But the enigmas are those that break the mold. Take, for instance, an otherwise unremarkable star over 1,000 light-years away in the constellation Cygnus, which suddenly began dimming in irregular and dramatic fashion on wikipedia.org. At its oddest moments, this star lost nearly a quarter of its light in wikipedia.org, as if an enormous shadow periodically swept across it. Astronomers worldwide were captivated. They nicknamed it Tabby's star, and for good reason. It became one of the most mysterious stars in the Milky Way, defying easy explanation. Normally, a dip in starlight suggests something like a planet or a dust cloud crossing in front of the star. But a planet small enough to be unseen could never block so much light, and a dust cloud thick enough to dim the star by 22% should have left other clues. The star's brightness didn't just dip once, it dipped multiple times, by different amounts, and for irregular durations. It brightened again in between, almost taunting those who tried to predict its next move. Scientists scrambled to find a cause for these bizarre light fluctuations. Could the star have devoured a planet, sending up billowing clouds of debris that occasionally veiled it carnegiescience.edu, or was there a swarm of comets breaking apart in orbit, throwing enough dust our way to briefly eclipse the starlight carnegiescience.edu? One imaginative hypothesis even proposed a colossal alien megastructure orbiting the star, intermittently harvesting its energy and casting a shadow toward Earth carnegiescience.edun.wikipedia.org. This idea captured the public's imagination, a Dyson sphere under construction perhaps, but evidence soon pointed back to more natural explanations. Still, none of the natural theories have perfectly fit the observations in .wikipedia.org. As more data rolled in, Tabby's star continued to perplex. Not only did it dim at strange intervals, it also seemed to slowly fade overall during the years of monitoring, then at times inexplicably surge brighter, carnegiescience.edu. It's as though the star were breathing in an erratic pattern, leaving astronomers to wonder what could be causing such chaos. To this day, Tabby's star remains an open riddle, a reminder that even a fairly ordinary star can surprise us with phenomena we've never seen before. And Tabby's star is not alone. In the constellation of Pisces, another strange star has been observed winking at us in an unpredictable way. Every so often, this star's light dips drastically, up to tenfold, for days at a time, nasa.gov. The star, named RZ Piscium, gives off far more infrared glow than a typical star of its kind, nasa.gov, a telltale sign that it's surrounded by a thick cloud of warm dust. What could produce so much dust around a single star? One clue came from the duration and depth of the dimming events, which hinted that massive clumps of matter were orbiting the star and occasionally blocking its light, nasa.gov. Researchers investigating RZ Piscium found evidence suggesting that the star might be devouring the remnants of its own planetary system, nasa.gov. Perhaps a giant planet ventured too close and was ripped apart, or a collision of planets left behind a swirling wreckage. The winking of the star could be the result of huge dusty fragments from this devastation, periodically drifting in front of the star and casting a shadow our way. In one scenario, a large planet could be slowly disintegrating under the star's heat and tidal forces, shedding streams of gas and dust that intermittently eclipse the starlight nasa.gov. It's a cosmic drama, a star consuming its offspring, surrounded by a funeral veil of dust. Some astronomers think RZ Piscium might be an aging star transitioning into a red giant, which as it expands would engulf any close-orbiting planets, nasa.gov. In doing so, the star could shred those worlds into clouds of debris, explaining the excess dust and the irregular dimming. Alternatively, it might be a younger star with a hyperactive asteroid belt, where frequent collisions create dust clouds. Intriguingly, RZ Piscium shows signs of being both youthful and mature NASA.gov, an object that doesn't fit neatly into our usual categories, straddling two stages of stellar life. These cases teach us that a star's light can be anything but steady. Even giant stars can have their mysterious dimming episodes. In late 2019, skywatchers were startled when Betelgeuse, the great red shoulder of Orion, began to fade dramatically. This star, a red supergiant nearing the end of its life, typically cycles through gentle brightness variations. But this time was different. Betelgeuse's luminosity plunged far outside its normal range, dimming so much that the familiar constellation looked visibly altered to the naked eye. For months, nobody was certain what was happening. Was Betelgeuse about to explode as a supernova? That tantalizing but alarming prospect hung in the air. Eventually, observations from multiple telescopes helped solve the mystery. Betelgeuse had belched out a colossal cloud of gas and dust, which cooled and condensed right in front of the star, temporarily obscuring a large portion of its light. In essence, Betelgeuse had partly hidden behind its own exhaled breath. The star gradually returned to its usual brightness after the dust dispersed, quelling the supernova fears. But for a while, we were reminded that even our brightest and most familiar stars can surprise us with sudden, puzzling behavior. From these flickering stars, astronomers have learned to expect the unexpected. They monitor such variable enigmas closely, collecting clues in the spectrum of starlight and the timing of each dip and swell. In some cases, patterns begin to emerge. A dust disk here, a companion object there. In others, like Tabby's star, the pattern resists deciphering, keeping its secrets hidden in plain sight. These stars challenge our understanding of how stable we thought stars generally were. Instead of steady beacons, they behave more like cosmic lighthouses, sending distress signals or undergoing convulsive changes. Are we witnessing rare phases of stellar evolution? Starquakes or magnetic disturbances across their surfaces? Or interactions with unseen companions, planets, stars, or swarms of comets that create these irregular light shows? Each hypothesis invites further observations to confirm or refute it. And as new telescopes come online, capable of monitoring millions of stars, who knows how many more oddballs like these we will find? The Milky Way might be sprinkled with stars that flicker and swell in baffling ways, each a puzzle piece for astrophysicists to ponder. Floating in the darkness, these inconsistent stars remind us that the story of a star is not always a simple arc of birth, steady shining, and quiet demise. Sometimes there are unexpected twists, sudden dimmings, wild flares, or periods of unsteady output that make us question what we know about stellar physics. We've learned that where there is variation, there is information. Each flicker can whisper something about internal forces or external companions. But for now, as we watch the erratic blinking of stars like Tabby's star or RZ Piscium, we continue to gather data, waiting for the moment when the riddle will unravel. Until then, these variable enigmas keep their secrets, flickering in the cosmic night like distant candles in the wind. Far from the solitary quirks of single stars, in the dense gatherings of star clusters, another stellar mystery arises. Among the myriad suns packed together in globular clusters or loose stellar families, one would expect a consistent story of aging. All the stars born at roughly the same time, aging in unison like siblings. Yet astronomers looking at these clusters found something astonishing. Interlopers that look conspicuously young and hot among a crowd of elders. These standout stars burn with a brilliant blue-white light, the hallmark of youth, even though they dwell in clusters known to be ancient. They are called blue stragglers, and their very presence poses a tantalizing riddle. By all logic, these stars should have long ago aged and mellowed, possibly swelling into red giants, or even dying off. Instead, they lag behind in the aging process, appearing as youthful stragglers in an otherwise old stellar population and .wikipedia.org. It's as if in a classroom of senior citizens, a few students suddenly look like spry teenagers. How did they manage to stay so young-looking in such an old crowd? The discovery of blue stragglers dates back to the 1950s, when astronomers noticed this anomaly in a globular cluster's color magnitude diagram. Normally, in a cluster, the stars line up in a neat sequence according to their mass and age. The more massive ones, having lived fast and died young, would have already left the main sequence, drifting into later life stages. The cluster's HR diagram, a kind of family portrait of star life, would have a clear cut-off point marking the cluster's age. But blue stragglers sit above that cut-off, shining as if they were more massive and younger than they should be. Wikipedia organ. Wikipedia.org. For a long time, their origin was a complete mystery. Did they somehow form later than the rest of the cluster, perhaps by a second burst of star formation? That seemed unlikely in the tranquil environment of an old cluster. Or could they be aliens? Stars that didn't originally belong to the cluster at all, but wandered in from outside. Yet blue stragglers often lie right at the cluster's heart, as though they've been long-time residents and .wikipedia.org and .wikipedia.org. Over the years, scientists pieced together clues and developed a consensus on how blue stragglers likely gain their second lease on life. The key, it turns out, is not that they were born later, but rather that they were reborn. In the dense crowds of a star cluster, close encounters are inevitable. Stars can collide or interact in tight binaries. Imagine two aging stars in a binary system drawing ever nearer, or perhaps even crashing into each other. If they merge, the combined star suddenly has fresh fuel and a higher mass, effectively rejuvenating item.wikipedia.org. This merger product would burn hotter and bluer, masquerading as a young star. Likewise, if two stars don't fully merge, but one feeds mass to the other, the recipient star bulks up and is re-energized. It's akin to a cosmic facelift. The star appears young again by gaining mass that wasn't originally its own. Observations support both scenarios. In some clusters, blue stragglers are more common in the crowded core, where collisions would be frequent, hinting that head-on mergers play a role in .wikipedia.org. In other cases, blue stragglers inhabit the cluster's outskirts, where direct collisions are rarer, suggesting a binary mass transfer origin out there in .wikipedia.org. One star in a binary evolves faster, swells up, and spills its material onto its companion. The donor star, having shed much of its mass, ends up as a dim relic, perhaps a white dwarf, while the accretor becomes an anomalously massive bright blue star, a blue straggler. This vampire star scenario paints blue stragglers as cosmic tricksters that have effectively cheated aging by siphoning life from a partner. What's fascinating is that both pathways, collisions and mass transfer, could be operating simultaneously. Studies of certain clusters show evidence for two separate groups of blue stragglers, potentially corresponding to the two different origins on .wikipedia.org. the ones lurking in the core, spinning rapidly and often showing signs of unusual chemical makeup, might be merger products. Meanwhile, those further out with telltale companion stars, like faint white dwarfs detected orbiting them, are likely former binaries that went through a dramatic case of stellar cannibalism. Wikipedia.org. In either case, the outcome is the same: a star that appears far younger than the rest of its peers. Even knowing these explanations, blue stragglers haven't entirely given up all their secrets. There are subtler questions. For instance, why do some clusters manage to have so many more blue stragglers than others? Are there blue lurkers, stars that have gained some mass, but not enough to stand out, hiding in plain sight among the population? And could similar rejuvenation happen in smaller groups, or even in our galaxy's general field of stars? Indeed, astronomers have identified a kind of field blue straggler among isolated stars in the galactic Halloween.wikipedia.org. The telltale signs are there if you know where to look: unusual chemical patterns, or fast rotation, betraying a history of mass exchange or merger. It appears that even outside of clusters, binary stars can produce rejuvenated stars, given enough time and the right circumstances. From a broader perspective, blue stragglers teach us about the social lives of stars. Star clusters are not just static swarms of points. They are dynamic environments where stars can interact, sometimes violently. In the crowded ballroom of a globular cluster, stellar encounters can lead to dramatic makeovers, and the blue stragglers are the living proof. They remind us that in astronomy, as in life, appearances can be deceiving. A star that looks young and vibrant may carry the history of a cosmic collision or a vampiric feeding in its core. These stars once perplexed astronomers by flouting the expected rules of aging, but now we see them as natural products of second chances, stars that refuse to grow old on schedule. Having peered into the secret of youth stolen among the stars, we turn to another elemental puzzle. Deep in the hearts of stars, nuclear reactions forge most of the elements we know. Some elements are eagerly consumed in the stellar furnace, never to be seen again on the stellar surface. One such element is lithium, a fragile metal that on Earth is used in batteries, but in stars has a very short lifespan. Lithium burns up at relatively low temperatures. In the deep interiors of stars, any lithium present is quickly destroyed in nuclear reactions. By the time a star ages and swells into a red giant, any original lithium it had should be long gone, diluted away, or fused into heavier elements and org. And yet, astronomers have found something perplexing. Certain stars, especially some swollen red giants, show inexplicably high amounts of lithium in their spectra. This is the lithium puzzle, a chemical oddity that seemingly shouldn't exist in stellar cores or atmospheres, but does. When this anomaly was first noticed, it left astronomers scratching their heads. These lithium-rich giant stars were essentially flaunting a trait they weren't supposed to have, and a .org. It was as if an aging candle flame suddenly started emitting a scent of fresh pine, clearly out of place given what we expect in the late stages of a star's life. In stellar terms, a red giant's outer layers are made of material that has been cooked and churned deep inside the star. During that cooking process, lithium should be one of the first ingredients to burn away. So finding a red giant with an abundance of lithium is like finding ice cubes floating in a pot of boiling water, a sign that something unusual must have happened to put them there, or to keep them intact. Scientists have proposed several ideas to explain this inconsistency. One hypothesis suggests that some red giants might manufacture lithium in situ under rare conditions. For example, during a brief phase in a giant star's life, there could be a mixing event that dredges up helium from the core into a region where it undergoes a fusion reaction, known as the Cameron-Fowler mechanism. that momentarily creates lithium, which is then transported to the surface before it can be destroyed. If timed just right, the star might sport a surge of lithium in its outer layers, like a transient rash on a star's skin. Another possibility is even more dramatic. Perhaps the star engulfed a lithium-rich planet or brown dwarf. Imagine a giant star swelling and pulling in a nearby planet that's rich in lithium, since planets and young brown dwarfs haven't had their lithium burnt away. As that planet spirals into the star and disintegrates, it could deposit its store of lithium into the star's outer envelope, briefly spiking the lithium content. Observational evidence lends some support to this idea. Stars with high lithium often also show signs of having recently ingested something. Unusual rotation rates or peculiar chemical mixes that hint at a disrupted system. Such an event would indeed be a case of a star seasoning itself with its own planet's material. However, studies suggest that planet engulfment alone might not account for all lithium-rich giantsias. .ac.insciencedirect.com. Not every lithium-rich star shows the expected telltales of a recent planetary feast. This has led astronomers to suspect that multiple mechanisms could be at play. Some giants might get their lithium from internal fusion-driven production, while others gain it from swallowing planets, and perhaps some from a combination of smaller events. It's a complex puzzle where different pieces might fit for different stars. The difficulty is compounded by the fact that lithium is so fleeting in the stellar context. Any lithium that appears won't last long unless conditions are just right to preserve it. So catching a star in the act of being lithium-rich is catching a brief moment in time. Interestingly, the lithium puzzle isn't confined to evolved stars. There's also a long-standing cosmological lithium problem regarding the lithium content of the oldest stars in the galaxy. The universe's very first few minutes, during the Big Bang, forged some lithium along with hydrogen and helium. Models of Big Bang nucleosynthesis predict a certain primordial abundance of lithium. Yet when we look at ancient stars in the galactic halo, nearly pristine fossils of the early universe, we find they have significantly less lithium than expected. This discrepancy between predicted and observed lithium in the oldest stars remains an unresolved issue in astrophysics. link.aps.orgssciencedirect.com. It's as if the universe itself somehow hid away or destroyed a portion of its initial lithium before it could end up in those stars. Or perhaps our theories of those first few minutes of creation need adjusting. Some exotic solutions have been proposed, ranging from tweaks in nuclear reaction rates to entirely new physics. For example, decaying particles in the early universe that might selectively gobble up lithium. Link.aps.org. Whether on the cosmic scale or within individual stars, lithium keeps showing up where, by rights, it shouldn't, and conversely, not showing up where it should. Each lithium-related mystery reminds us that there's nuance in how elements are made and distributed across the cosmos. In the case of stars that regrow a veneer of lithium late in life, it tells us that stellar evolution has surprise twists. Late-stage convection or external ingestion can alter a star's makeup in ways we hadn't anticipated. The lithium puzzle has driven astronomers to scrutinize stars with high-resolution spectrographs, looking for the subtle fingerprints of this element and others that might accompany it. Little by little, they are piecing together the circumstances that allow a star to flaunt this forbidden chemical signature. Perhaps soon, with new surveys examining millions of stars, we'll have enough examples to pin down the cause. Until then, the sight of a lithium-rich star remains both a surprise and a clue, a chemical message from the star's past, hinting at an unusual chapter in its life story. From puzzling chemicals to perplexing measurements, our journey now leads us to a stellar conundrum that has implications for the scale of the cosmos itself. For many decades, certain stars known as Cepheid variables have been our steadfast beacons for measuring cosmic distances. These luminous giants pulsate in and out like beating hearts, and their pulsation periods relate directly to their intrinsic brightness, a discovery made over a century ago that turned them into cosmic mile markers. By comparing how bright a Cepheid appears from Earth to how bright it truly is, as indicated by its period, astronomers can gauge its distance. This period luminosity relationship has made Cepheids one of the cornerstones of the cosmic distance ladder. They are, in essence, clocks and yardsticks combined. Their rhythmic brightening and dimming not only tell time, but also tell distance. Yet even these reliable standard candles have presented an anomaly in recent times. As astronomers have refined their measurements to unprecedented precision, they've uncovered a slight but nagging discrepancy, a conflict in the readings of our cosmic expansion, depending on which yardstick is used. Cepheids are at the heart of this riddle. When Cepheid-calibrated distances are used to determine the Hubble constant, the rate at which the universe is expanding, the answer comes out higher than when that rate is inferred from other methods, like observations of the cosmic microwave background. In simpler terms, the universe appears to be expanding faster when measured by Cepheid-based techniques than it does when measured by the afterglow of the Big Bang. This is often referred to as the Hubble tension, an intriguing mismatch between the cosmic scales mathscholar.org. For a while, scientists wondered if Cepheids themselves might be the source of the discrepancy. Could it be that our Cepheid distance measurements were off? Perhaps Cepheids in other galaxies behave slightly differently due to environment or composition. Cepheids come in different types. Classical Cepheids, young, massive population I stars, and Type 2 Cepheids, older, population 2 stars, and confusing one for the other could introduce errors if not accounted for. There are also subtleties like the effect of heavy elements. A metal-rich Cepheid might be a tad fainter or brighter than a metal-poor one of the same period, skewing distance calculations if one isn't careful. Astronomers have worked hard to calibrate all these effects, using nearby Cepheids whose distances can be measured directly via parallax, or observing Cepheids in star clusters where other distance indicators are available. Despite these efforts, the tension has persisted. mathscholar.org. If the Cepheids are not at fault, perhaps the anomaly lies in new physics. Maybe the universe's expansion history has an unexpected twist. Perhaps the influence of dark energy changed over time, or there are subtle relativistic effects at play that we haven't accounted for. Or it could be that some other rung of the distance ladder has an issue. After all, Cepheids calibrate Type Ia supernova distances, and those supernovae underpin the Hubble constant measurement. On the other side, the cosmic microwave background analysis assumes our standard cosmological model. A mismatch means somewhere something is not aligning. It's a bit like measuring a table with two different tape measures and getting two slightly different lengths. Either one tape is stretched, or the table isn't as straight as assumed. The Cepheid anomaly has encouraged astronomers to double down on cross-checking the cosmic distance ladder. New observations from the Hubble Space Telescope and now the James Webb Space Telescope have been used to observe Cepheids in distant galaxies with even greater clarity. Red giant stars, via the tip of the red giant branch method, offer an independent alternative for distance. Interestingly, their measurements tend to fall between the Cepheid-based result and the cosmic background-based result, adding another piece to the puzzle mathscholar.org. This only deepens the intrigue, as if the universe were giving us clues, but not the full solution. One thing is certain. The Cepheids themselves, as stars, haven't done anything wrong. They still obey the period luminosity law faithfully in our galaxy and nearby ones. The anomaly is in how we interpret their message. versus the story told by other cosmic indicators. It's an ongoing detective case in astronomy. Each new data release, whether from space telescopes or ground observatories, is like fresh testimony, and scientists are carefully weighing it to see if the discrepancy grows or fades. This particular puzzle carries weighty consequences. The rate of cosmic expansion ties into the age of the universe and the physics of what's driving the acceleration, like dark energy. If Cepheids are telling us the expansion is faster than expected, it could imply that our standard cosmological model is missing a component, maybe an extra particle species, or a subtle revision in how gravity works on large scales. On the other hand, if the issue is observational, say, something like Cepheids in distant galaxies being dimmed by dust in ways not fully corrected for, then resolving it will refine our techniques but leave our cosmology intact. For now, scientists have humorously dubbed it a tension rather than a full-blown crisis, and they relish the possibility that this discrepancy is pointing toward new discoveries. After all, anomalies are often where breakthroughs hide. Even beyond this grand tension in cosmic measurement, Cepheids harbour subtler enigmas. These stars are famed for keeping steady time with their pulsations, but some have been caught slipping off beat in ways we don't fully understand. Arxiv.org. Every Cepheids period can slowly change over the centuries as the star evolves. But here, we're talking about irregular or unexpected changes superimposed on that evolution. A few Cepheids show slight but puzzling deviations in their rhythm. Perhaps the peak brightness comes a bit too early or late on occasion, or the interval between pulses drifts over the years. In essence, even the universe's most dependable metronomes can sometimes skip a beat. Astronomers are studying these deviations carefully. One possible explanation is that an unseen stellar companion is tugging on the Cepheid, causing its light pulses to arrive at uneven intervals as the star moves toward or away from us. A light travel time effect. In such a case, the Cepheid isn't truly changing its pulse. It just seems irregular because it's on a subtle orbit. Indeed, some Cepheids have been found to be in binary systems using this exact method. But other Cepheids exhibit more random period fluctuations with no evident pattern. Arxiv.org. This could hint at some internal process in the star, perhaps turbulent convection in its outer layers or magnetic activity, that slightly modulates the pulsation period. It might also be that we are catching a star in the middle of a transition between pulsation modes, causing temporary irregularities. Whatever the cause, these period slips are a reminder that we may not entirely know every nuance of how Cepheids tick. For the purposes of measuring distances, these anomalies are thankfully small and rare, so Cepheids remain very reliable yardsticks overall. But to the astronomer intrigued by stellar physics, a Cepheid that won't perfectly keep the beat is an invitation to dig deeper. Studying these cases can reveal subtle effects in stellar interiors or binary interactions that would otherwise escape notice. Just as a clockmaker learns from the slight imperfections in a clock's timing, scientists use these Cepheid oddities to refine their understanding of the inner workings of stars. It keeps us alert. Even our trusted standard candles have secrets. Each irregular heartbeat of a Cepheid could be whispering a clue about something like a hidden companion or a nuance of pulsation physics not yet fully accounted for. It's yet another instance of the cosmos, reminding us that no object is truly simple when examined closely. And even a star's steady rhythm can hold surprises that challenge us to explain them. From stars that serve as cosmic yardsticks, we move to stellar relationships that test the boundaries of gravitational choreography. In the grand ballet of the galaxy, stars often come in pairs or groups, bound by gravity and locked in orbital dances. Most binary stars follow well-understood steps. one orbiting the other in stable ellipses, like a waltzing couple. But introduce a third partner, and the dance can become wildly complicated. Odd pairs and triplets of stars exist that challenge what we think is a stable configuration. In fact, as a rule, 3 or more stars gravitationally bound to each other live in a potentially chaotic arrangement. The general three-body problem has no simple solution. Their orbits can be intricately intertwined and prone to disturbances. That's why we usually find multiple star systems in hierarchical setups. For instance, 2 stars orbiting very closely, while a third orbits far away, so each pairwise dance is mostly undisturbed by the third. Even so, astronomers have discovered some multiple star systems that appear to defy these stability expectations. Imagine a tight-knit binary being circled by a third star not much farther out. You have a triplet where the gravitational tugs are complex, and the orbits might change over time in unpredictable ways. There are even quadruple or higher systems, essentially mini-star clusters, holding together in delicate balance. One famous example is Castor in the constellation Gemini. What looks like a single bright star is actually a sextet. 6 stars, linked in a gravitational dance of 3 binary pairs. Each binary pair orbits its own common center, and those 2 centers orbit each other in turn. It's a cascading arrangement that remains stable as long as the distances and mass ratios are just right. But it boggles the mind that nature can maintain such an intricate structure for eons. The most precarious multiple systems are those on the edge of instability. Sometimes we find a triple star system where the outer star's path is highly elongated, swinging much closer at one part of its orbit before retreating far away, almost daring the system to break apart. During those close approaches, its gravity can significantly perturb the inner binary, changing the timing of their eclipses or altering their orbital shape. One outcome of such interactions can be a flip in orbital planes or a periodic oscillation of eccentricity, phenomena known as Kozai-Lidov cycles. Through these cycles, a once stable orbit might become very eccentric or tilted, potentially sending one star of the trio plunging inward or flinging it out of the system entirely after enough time. When astronomers run computer simulations of 3 stars under gravity, they often see one star eventually get booted out, a likely reason why many stars end up alone. So whenever we observe a long-lasting triple, especially a compact one, we know we're looking at something special, a configuration that has somehow managed to avoid the typical fate of chaos for longer than expected. Consider a system like HD 98800 in the constellation of TW Hydrae. It's a quadruple system composed of 2 pairs of stars, each pair orbiting around a mutual center. One of those pairs has a prominent disk of dust around it, oriented at a wildly different angle from the orbit of the pair around the other. It's as if one pair of dancers twirls with a hula hoop around them, while another pair circles on a tilted stage. How did it end up like this? Perhaps gravitational nudges over time twisted the disk, or maybe the system didn't form altogether, but is a capture of stars that originated elsewhere. Another curious example is Iota Cassiopeiae. Through a telescope, it resolves into 3 stars, 2 tightly bound in a close dance, and one more orbiting at a distance. The intricacies of their orbits took decades to untangle, requiring patient observation to understand which star was moving where. They appear stable now, but we know such balance is delicate. A slight change in their past motions could have made the system fall apart. The oddest multiples can even include contact binaries within them. 2 stars so close that they share an atmosphere, essentially touching and continuously exchanging matter, all while a third companion orbits them both. These systems are astrophysical laboratories for extreme star interactions. The inner pair, being so close, might one day merge, and the presence of the third star could influence when or how that happens. We know that in some triples, the third star can induce those Kozai oscillations that periodically crank up the inner binary's eccentricity, possibly driving the two inner stars into each other at some point. So a triple system can be not just a picturesque dance, but sometimes a ticking time bomb leading to a stellar collision, or even a future supernova, all orchestrated by gravity's subtle interplay. What's remarkable is that even in these precarious systems, nature finds temporary harmony. They might endure for millions or even billions of years before any catastrophic instability manifests. In the meantime, they challenge our simulations and understanding. Every unusual triple or quadruple we spot is a chance to test what we know about gravitational dynamics. Do our models predict the orbits we actually observe? Often they do, but sometimes there are surprises. Perhaps one star is moving faster than expected, or an orbit is tilted in a way that pushes the boundaries of stability. By studying these, astronomers refine their grasp of how star systems form and evolve. Some odd multiples might be relics of a larger cluster that dissolved, leaving behind a few stubbornly bound survivors. Others may be young systems that haven't yet settled. Given more time, one member might be ejected, turning a triple into a stable binary, plus a single runaway star. From the chaotic dances of multiple stars, we cast our eyes to the lonely travelers of the galaxy, the rogue wanderers, planets without homes. We often imagine planets as inseparable companions of stars, locked in orbit under their sun's warm glow. But astronomers have realized that countless planets may roam interstellar space on their own, dark, free-floating orbs that belong to no solar system. These rogue planets drift in the eternal night, only faintly lit by whatever distant starlight they reflect, or by their own residual heat. They are nearly invisible to us, except through rare and subtle effects, making them mysterious spectres of the galaxy. How do planets end up alone, cast away from any star? The leading theory is violence in their youth. In the early days of a planetary system, the orbits of nascent planets can be chaotic. Giant planets might jostle for position, gravitationally slingshotting each other into new paths. If one planet comes too close to a much heavier sibling, or if a passing star perturbs the system, a planet can be flung out entirely, banished from its birthplace. Imagine a cosmic game of billiards. One wrong angle, one strong gravitational kick, and a planet finds itself ejected, sent hurtling into the void between the stars. Once free, it wanders the galaxy, a tiny world adrift in a vast, cold ocean of space. Another possibility is that some rogue planets are born free. Stars and planets form from collapsing clouds of gas. Usually the leftover material around a newborn star coalesces into planets. But if a clump of gas is too small to ignite as a star, and yet not part of any protostellar disk, it might form a solitary object, essentially a failed star that is, by mass, a giant planet. Such an object would never have a parent star. Whether cast out or born alone, the number of rogue planets out there is expected to be staggering. Estimates have varied, but some studies suggest there could be on the order of billions or even trillions of these orphan worlds in our milkywayspace.com. One recent analysis even posited that there might be roughly 20 rogue planets for every star in the galaxyspace.com, meaning that, if true, the rogues far outnumber the stars themselves. Detecting these lone worlds is a formidable challenge. Because they emit little to no visible light of their own, aside from a faint heat glow, especially if they are still young or geologically active, rogue planets don't announce themselves easily. Astronomers have turned to a clever method called gravitational microlensing. If a rogue planet happens to pass in front of a distant background star from our viewpoint, the planet's gravity can bend and focus the star's light like a lens. We observe the star briefly get brighter in a very specific pattern that reveals the presence and mass of the unseen foreground planet. Such microlensing events are rare and fleeting. One must monitor millions of stars continuously to catch a few, but they have provided tantalizing evidence of these invisible nomads. Through these surveys, scientists have identified candidates for rogue planets, including some with masses comparable to Jupiter and others possibly as small as Earth. Each detection is like a ghostly whisper, a brief brightening in a star's light. Yet it speaks volumes, confirming that free-floating planets are not just theoretical. The thought of these rogue wanderers sparks the imagination. Picture a lone planet drifting far from any sun. Its sky would have no sunrise or sunset, only an all-encompassing night with a faint, perpetual starlight glow. If it has an atmosphere or retains internal heat, perhaps it could even host some form of life in deep subsurface oceans or around hydrothermal vents. Life that knows nothing of stars or daylight, sustained by the planet's own warmth. These scenarios, while speculative, aren't entirely ruled out. Some rogue planets might even carry moons, forming a miniature system that journeys together through the galaxy. In the deep cold of space, a large moon orbiting a rogue planet could experience tidal heating if it's close enough, providing a trickle of energy. It's a fanciful idea, yet with potentially so many rogue planets out there, one wonders what odd realities might exist on some of them. Our exploration of these planetless worlds is just beginning. In the coming years, new instruments like NASA's Nancy Grace Roman Space Telescope are expected to find many more of these elusive objects. Earthsky.org, nasa.gov. Each new rogue planet discovered will add a piece to the puzzle of how planetary systems form and sometimes tear themselves apart. They also offer insights into the sheer abundance and variety of planets. Early indications from microlensing suggest a lot of the free floaters could be of relatively low mass, perhaps Earth-sized or smaller-space.com, which raises the possibility that the galaxy could be teeming with wandering Earths and super-Earths that we've yet to detect. The prospect challenges our conventional image of a planet tied to a parent star. Instead, we must envision a vast population of solitary worlds, each a tiny island unto itself in the interstellar sea. From the lonely life of rogue planets, we return to stellar companionship, but of a more sinister kind. In the grand tapestry of binary stars, not all companionship is benign. Often, one star can turn into a predator, siphoning gas from its partner in a dramatic act of stellar cannibalism. This can happen in various surprising ways, giving rise to phenomena that are both violent and fascinating. We've already touched on one gentle form of this, the mass transfer that creates blue stragglers. But stellar cannibalism can get far more extreme. Imagine a star so greedy that it pulls matter off the surface of its neighbour, creating a swirling accretion disk of hot plasma between them. The victim star, losing its life-giving fuel, may wither prematurely, while the feeding star grows invigorated and bloated. One classic example lies in the Algol system, an eclipsing binary that puzzled astronomers for generations. Algol consists of a bright, massive blue-white star and a dimmer, cooler orange star in close orbit. By conventional wisdom, the more massive star should have evolved faster and become a red giant by now, and the less massive star should still be on the main sequence. Yet in Algol, the situation is reversed. The massive star is still happily fusing away on the main sequence, while the less massive star has swollen into a subgiant. This is the famous Algol paradox. The resolution was the realization that the stars have exchanged mass in their pastastro.vaporia.com. The original primary star, initially the more massive of the two, exhausted its core fuel first and started to expand, but as it did so, its outer layers spilled over its Roche lobe and flowed onto its companion. In the process, the primary lost much of its mass to the secondary. The once smaller star gained this mass and rejuvenated into the hot blue star we see today, while the original primary was left stripped and reduced in mass, now appearing as the underweight, puffed-up orange subgiant astro dot vaporia.com. Essentially, the Algol system is a snapshot of stellar cannibalism in action. The smaller star turned the tables and ate its companion's envelope, and in doing so, it became the more massive of the pair. Stellar cannibalism can reach even more dramatic heights when the predator star is not a normal star at all, but a compact remnant. Consider a binary where one member is a white dwarf and the other is an ordinary star. As the normal star evolves and swells, the white dwarf's gravity can start pulling in its outer layers. Gas siphons off the giant star and spirals onto the white dwarf, forming a searing hot accretion disk. Over time, this stolen gas piles up on the white dwarf's surface. When enough has accumulated, it can ignite in a sudden thermonuclear burst, a nova, blasting material outward and causing a temporary surge in brightness. Remarkably, the white dwarf survives this outburst, and the cycle can repeat as it continues to feed. In more extreme cases, a white dwarf might accrete so much mass that it reaches a critical limit and detonates completely as a Type Ia supernova, obliterating itself. In those instances, the vampire star gorges to the point of self-destruction. Neutron stars and black holes, the ultra-dense remnants of massive stars, are perhaps the most voracious eaters. When paired with a living star, their immense gravity allows them to strip gas from their companion at a prodigious rate. The infalling matter forms an accretion disk and is heated to incredible temperatures, emitting powerful X-rays. These systems, known as X-ray binaries, showcase some of the most energetic phenomena in the galaxy. A neutron star with a strong magnetic field can channel the accreted gas onto its magnetic poles, producing intense beams of X-rays that sweep around as the star rotates. We observe these as X-ray pulsars. Black hole binaries, like the famous Cygnus X1, where a stellar mass black hole is feasting on a blue supergiant, create roaring torrents of radiation and sometimes jets of particles that shoot out at nearly light speed from the disk's poles. The violence of these interactions is hard to overstate. Gas plunges into an unseen gravitational well, heating to millions of degrees, releasing energy that can outshine entire star clusters in X-rays. Even among more ordinary stars, subtler cannibalistic behaviors exist. Some binary stars orbit so closely that their outer atmospheres touch and merge in what's called a contact binary. Here, the two stars share a common envelope and exchange mass freely. It's a more mutual form of communion, but often one star, the slightly more massive one, ends up being the dominant eater, growing at the expense of the other. Over time, and perhaps with some push from gravitational interactions with other nearby stars, such contact binaries might coalesce into a single star. The final coalescence can produce a transient glow known as a luminous red nova, not as catastrophic as a supernova, but a dramatic flare-up caused by the merging of two stars and the shedding of their combined outer layers in a reddish explosion. It's thought that some odd, isolated red flashes we've recorded in other galaxies were exactly this. Two stars, quietly orbiting each other, gradually spiraling in until one day they became one, announcing the event with a dusty red boom. Stellar cannibalism reminds us that in the cosmos, as in a wild ecosystem, energy and matter are constantly being redistributed. One star's gain is another's loss. By cannibalizing a neighbor, a star can extend its life and dramatically alter its evolutionary path. It might become an unusually blue star in an old environment, like a blue straggler, or it might set off spectacular fireworks, like novae and supernovae. The victim star's fate is drastically changed. It can be stripped to a mere core, end up as a faint helium star, or be pushed into an exotic state it wouldn't have reached alone. On a grander scale, these interactions enrich the surrounding space. The material blown off in novae and stellar mergers carries heavy elements forged in stardust, seeding future generations of stars and planets with ingredients like carbon and oxygen. Through careful observation of these violent stellar affairs, astronomers learn about fundamental physics under extreme conditions. Each X-ray flare from an accreting neutron star, each repeat nova from a feeding white dwarf, each strange orbital dance in systems like Algol is a piece of the puzzle. By measuring orbital periods and sudden outbursts, we can infer the masses of stars and the rate of mass exchange. By detecting the gravitational waves from the rare star mergers or the specific light from a supernova, we test our theories of gravity and thermonuclear runaway. These cannibal stars, destructive as they are to their companions, have been generous to science, providing natural laboratories that push the limits of what matter can do under intense gravity, and helping us refine our understanding of stellar evolution in binary systems. After considering stars that break the rules or break their companions, you might think we've plumbed the depths of stellar strangeness. But even the dependable rhythms of stars can hold surprises. Returning to Cepheid variables for a moment. Earlier, we saw how their pulsations serve as cosmic clocks and yardsticks. In most cases, a Cepheid's pulse period is stable or changes only slowly as the star ages. However, some astronomers examining long-term records noticed that a few Cepheids aren't keeping perfectly steady time. Their pulsation periods, tracked over decades, can show unexplained shifts, arxiv.org. These are not the gradual, predictable changes from stellar evolution, which we do often see. For example, a Cepheid might slowly lengthen its period over centuries as it expands. Instead, these are more erratic fluctuations, sometimes abrupt or cyclic, that don't match what we'd expect from a smooth evolutionary trend. It's as though a reliable clock has developed a subtle jitter. One potential cause for a Cepheid's clock to drift is the presence of a companion star. If a Cepheid is in a binary system, its light will sometimes take a little longer or shorter to reach us, depending on where it is in its orbit. This can make the pulsations appear to come slightly late or early in a periodic way. In fact, this light travel time effect has been used to discover Cepheids that are orbited by another star. The pulsation timing betrays the wobble of an unseen partner. But not all cases of period drift fit such a neat periodic pattern. Some Cepheids have irregular or non-cyclic changes that are harder to explain. Perhaps these could be due to changes within the star itself. For instance, a hiccup in its pulsation mode, or a temporary change in its structure. Cepheids are dynamic stars, with hefty flows of energy in their outer layers, and it's conceivable that convection or other processes could introduce a bit of noise into their otherwise regular beat. Though these anomalies in Cepheid timing are small, they fascinate astronomers. Why would a star renowned for consistency deviate at all? Investigating this could deepen our understanding of pulsation physics. It might reveal, for example, a previously unknown kind of pulsation interference, or a resonance that occasionally disrupts the main period. Or it might highlight the effect of a second pulsation mode. Some Cepheids can pulsate in two modes at once, beating against the primary one to cause minor period modulations. There's even the possibility that we're seeing the Cepheids' evolution in real time, perhaps a rapid phase where the star's internal structure is changing quickly, causing a noticeable period change over human timescales. For now, the Cepheid clocks that drift are a small curiosity, not a challenge to their utility in measuring distances, but a reminder of the richness of stellar behavior. Each Cepheid that misbehaves is like a case study, a star to watch more closely, to model in detail, and to learn from. Already, these studies have uncovered several Cepheids in binary systems and given insights into how common such companions re-arxiv.org. They have also shown that irregular period changes are fairly widespread, hinting that maybe every Cepheid has a bit of personality once you measure it long enough. In the end, even a standard candle star isn't just a beacon. It's a physical object with its own life story, one that can include subtle surprises. All the phenomena we've explored so far involve normal stellar processes: gravity, nuclear fusion, orbital dynamics, or stellar evolution, even if taken to extremes. But what about a star that challenges the very definition of a star? Imagine an object that shines, however faintly, without the heat of fusion at its core. A star that glows, but not because it is burning fuel in the traditional sense. Such a concept sounds like an oxymoron. How can there be light without the fire? Yet theorists have proposed the existence of just such an object, sometimes dubbed a dark dwarf or dark matter star. These would be among the faintest, coldest stars, powered by an entirely different energy source: the annihilation of dark matter particles deep within them. ScienceDaily.com. Dark matter is the mysterious substance that makes up roughly a quarter of the universe's mass energy content, yet it neither emits nor absorbs light. We know it exists only from its gravitational effects on galaxies and galaxy clusters. It's thought to form a vast halo around our Milky Way, with the density increasing toward the galactic center. Normally, dark matter particles pass through ordinary matter and through each other without a trace. But if dark matter is composed of certain kinds of particles, for example, the hypothetical WIMPs, weakly interacting massive particles, then occasionally those particles could collide and annihilate each other, releasing energy. In a place like the core of a star, particularly a star that isn't hot enough to sustain fusion, this dark matter annihilation could become a primary heat source. ScienceDaily.com, ScienceDaily.com. A dark dwarf would be a small, faint star, perhaps only approximately 8% of the Sun's mass, below the threshold for hydrogen fusion, that nonetheless emits a dim glow thanks to dark matter continuously streaming into it and annihilating in its interior. How might such a star come to be? It's conjectured that in regions where dark matter density is extremely high, say the inner core of our galaxy, or in dense dwarf galaxies, even normal stars might capture significant amounts of dark matter. A brown dwarf, a failed star not massive enough to ignite fusion, in such an environment could accumulate a reservoir of dark matter in its center. Instead of gradually cooling and fading to a barely visible ember, it would be kept warm by the continuous drip of dark matter annihilation energy. In effect, the dark matter would replace hydrogen fusion as the heater of the star's core. The result? A star that glows without heat in the usual sense. Its light is not from a hot fusion furnace, but from an invisible hearth of particle annihilation. If such objects exist, how could we identify them? They would likely look much like ordinary faint stars or brown dwarfs. But there are a couple of potential telltales. One involves lithium, that fragile element we discussed earlier. In a normal brown dwarf or low-mass star, any lithium present from its formation either remains, if the object is too cool to burn it, or gets quickly destroyed once core temperatures exceed about 2.5 million Kelvin. A dark dwarf, however, would have an unusual thermal history. It might stay cooler internally, since it's not undergoing intense fusion. So if it started with lithium, it could retain it longer than expected. Yet at the same time, it could be more luminous than a typical brown dwarf of the same age because of the extra dark matter heating. So imagine finding a dim, star-like object that is brighter than its temperature and age suggests it should be. And upon analysing its spectrum, you see an unexpected preservation of lithium, which a normal star of that brightness would have depleted. ScienceDaily.com, ScienceDaily.com. That combination might raise eyebrows as a candidate dark dwarf. So far, we haven't found a confirmed dark dwarf. They remain a speculative idea, albeit one grounded in serious physics and motivated by the tantalizing quest to identify dark matter. If we did discover one, it would be a breakthrough on multiple fronts, a new kind of star, and a direct window into the properties of dark matter particles. ScienceDaily.com, ScienceDaily.com. It would tell us that dark matter, which we usually think of as drifting inertly through space, can in the right circumstances clump and self-annihilate enough to influence normal astronomy. In a sense, it would blur the line between stars, which shine by releasing energy from their mass via fusion, and exotic compact objects, which could shine by tapping into the mass of dark matter. The idea of a star shining from exotic fuel like dark matter stretches our imagination. For over a century, we've defined stars by the process of fusion at their cores, transmuting elements and powering their radiance. Here we have a hypothetical exception, a star lit by the shadowy stuff that usually only reveals itself through gravity. It's almost poetic to think that the darkest matter in the universe could cause a star to shine. A gentle glow born of invisible particles meeting their end inside an otherwise cold star. If such dark dwarfs are out there, they might lurk in the hardest to observe locales, at the Milky Way's centre, shrouded by dust, or in dwarf galaxies, where dark matter outweighs normal matter by large factors. They would be rare gems to find, but their existence would answer profound questions about what dark matter is and how it behaves. Beyond dark dwarfs, one could muse about other forms of glow without heat. Could there be astrophysical objects that shine mainly by gravitational energy without fusion? Say, a star-like object kept warm purely by the contraction of gas or friction. Brown dwarfs, for instance, shine dimly for a time just by contracting under gravity, converting gravitational potential energy into heat, but they eventually cool. Or consider neutron stars. They don't have fusion, yet they can light up in bursts by tapping their intense gravity and magnetic fields. Recently, theorists suggested that neutron stars could potentially emit brief flashes of light through a gravitational resonance effect, essentially using their strong fields to convert gravitational energy into light. livescience.com. It's speculative and not yet observed, but it shows that once we open our mind to alternatives to fusion, many possibilities glimmer on the fringes of physics. In truth, the glow without heat mysteries push us to acknowledge how much we still don't know about the dark corners of our galaxy. We've catalogued billions of traditional stars, but if a few unconventional objects are out there, they'd be easy to miss, lost in the glare, or simply too faint and odd to stand out without careful analysis. It will likely take new technology or innovative search strategies to find them, if they exist. The James Webb Space Telescope, with its keen infrared vision, might just be able to detect the faint warmth of a dark dwarf against the cold backdrop of space, especially if such an object is relatively nearby. And upcoming surveys might catch telltale anomalies, perhaps a star that appears to violate the usual mass-luminosity relationship Our journey in this chapter has ranged widely, from stars that flicker for unknown reasons, to those that seem younger than they should be, to bizarre chemical signatures and hypothetical dark-fueled stars. Each phenomenon, whether firmly observed or purely theoretical, reminds us that the Milky Way is filled with wonders and questions. We've delved deep into the riddles at the heart of our galaxy's stars. Now, as we prepare to venture further outward, the stage broadens. The light of the Milky Way's dense core and spiral arms will begin to thin as we head toward the outskirts. In the next part of our voyage, we drift toward the outer edge of the galaxy, a more remote realm where the familiar gives way to the truly uncharted. The stars are sparser there, the nights even darker, and who knows what strange phenomena await us at the border between our galaxy and the great intergalactic void. With a calm spirit of curiosity, we continue onward, seamlessly, to explore the mysteries of the galactic rim. Out in the vast darkness of our galaxy, countless stars seem to wink and flicker. Most shine with reassuring steadiness, but a few behave like cosmic tricksters. Imagine gazing at a distant star that suddenly begins to dim for no obvious reason. Its once constant glow falters, as if some invisible hand is slowly turning down a celestial dimmer switch. Astronomers have watched just such a star, its light dipping mysteriously as if something huge passed in front of it. At first, even seasoned scientists were baffled. The star's brightness fell by a fifth, then by nearly a quarter, on no regular schedule. Some wondered if a swarm of comets or a shroud of dust could be eclipsing it. In hushed speculation, a few even whispered about alien megastructures, desperate for an explanation to match the strangeness of the sight. Over time, clues began to point toward more natural causes, perhaps drifting veils of cosmic dust. Yet the mystery isn't fully settled, and the star continues to keep its secrets. Each unexpected flicker is like a coded message from nature, one we have yet to decipher. The cosmos, it seems, loves to remind us that not everything out there follows a neat and simple pattern. It's telling that when faced with such a mystery, our imaginations run wild. In the case of that flickering star, a few voices even raised the possibility of alien architects, colossal structures orbiting the star, harvesting its energy and causing the dips in light. Scientists remained skeptical, of course, leaning toward dust or natural phenomena. But the mere fact that such an idea took hold shows how these stellar enigmas capture us. They invite speculation at the very edge of science and imagination, reminding us how little we truly know about what's possible out there. If that puzzle weren't enough, another star delivered an even greater astonishment. In the heart of the Milky Way, a giant star slowly faded to almost nothing, as if an immense shadow had swallowed it whole. For many months it dimmed and dimmed, until only a whisper of light remained, a staggering 97% of its shine gone. Then, just as mysteriously, the star brightened back to life. To this day, nobody knows for sure what eclipsed that lonely sun. Theories swirl in the silence of observatories. Perhaps a colossal ring of dust, or an orbiting dark companion, is periodically cloaking the star. Some researchers picture a planet-sized object with a thick, opaque disk drifting between us and that distant giant. But the truth remains as hazy as the dust itself, leaving astronomers to marvel at how an entire star could nearly vanish from view right before our eyes. It's a humbling reminder that even in our own galaxy, nature can stage dramas we never anticipated. Nor are these fluctuations always caused by something external eclipsing a star. Sometimes the star itself is the source of the mischief. There are stars that intermittently veil themselves in clouds of their own making, expelling carbon-rich dust that can briefly hide their light. It is as though the star coughs and surrounds itself with a smoky haze, dimming until the haze drifts away. One star, fittingly named R. Coronae Borealis, became famous for vanishing from view at unexpected intervals due to this very trick. To an observer on Earth, such a star seems to disappear and then return, a celestial game of peekaboo driven by the star's own breath. Not all of a star's surprises come as a flicker in the dark. Some come as a sudden blaze of light. Imagine a star that has quietly shone for ages, suddenly erupting in brilliance. In the mid-19th century, a star in the southern sky astonished those watching. It flared until it outshone almost every star in the heavens. For a brief time, this once modest point of light became the second brightest star visible. And then, just as inexplicably, it faded away into obscurity over the years that followed. Even in recent times, we have witnessed stars swell in such outbursts. In 2002, a remote star unexpectedly became hundreds of thousands of times brighter than our sun. It was as if a cosmic beacon had been lit, casting dazzling light into surrounding space. Telescopes captured a haunting vision, rings of light expanding outward, reflections from the star's sudden flash echoing through interstellar dust. Then, after a few brilliant months, the star dimmed back down, leaving behind more questions than answers. What could cause such a burst of stellar fireworks? Some suspect two stars might have collided and merged, unleashing a flood of energy. Others propose that the star reached a late, unstable phase of life, casting off its outer layers in a dramatic belch of brilliance. The true cause remains a topic of lively debate. Watching these stellar eruptions is like seeing a star being momentarily reborn or reimagined, a fleeting spectacle that hints at violent processes hidden beneath its surface. From stars that wink out unexpectedly to those that swell in sudden glory, these variable enigmas keep astronomers on their toes. They remind us that even with centuries of sky watching, the heavens can still catch us by surprise. Each flicker, each flare, is a clue and a mystery, urging us to look closer and think harder. And as we puzzle over these capricious stars, other cosmic riddles await, some hiding not in how a star changes, but in what it appears to be. For the stargazer, there is something almost emotional about witnessing a star change its light. It's a reminder that the night sky is not a fixed portrait, but a living, shifting story. These flickers and flares whisper to us that even the stars, steadfast as they seem, experience their own kind of life, with quivers, outbursts, and quiet spells. And in those celestial fluctuations, we sense a connection across space and time, as if the universe is communicating in a subtle Morse code that we are just beginning to understand. Far away in the Milky Way's ancient star clusters, a different kind of mystery unfolds. Picture a swarm of stars born together billions of years ago, most of them now elderly and faint. They glow with a reddish hue, the telltale sign of advanced age and spent fuel. But nestled among these elders are a few startlingly bright blue stars, shining as if they are much younger than their neighbours. Their presence is unexpected and intriguing, like finding fresh young faces in a crowd of grandparents. If you look at a photograph of a typical ancient cluster, the blue stragglers are obvious once you know to seek them. They shine like sapphire beads sewn into a tapestry of golden stars. To astronomers, spotting these brilliant blue outliers in a sea of red giants was like finding spring flowers blossoming in the autumn, completely unexpected and out of season. The mere sight of them raised eyebrows and questions, because they clearly did not belong according to standard theories. These clusters are like retirement homes for stars, not nurseries. No new star should blaze blue there. Yet the blue stragglers persist, quietly telling us that under the right conditions, even old stars can find a way to shine like new. Astronomers were astonished when they first spotted these youthful-looking stars in old clusters. By all rights, such massive blue stars should have burned out eons ago in those environments. At first, some wondered if it might be an observational mistake, or a trick of blending starlight. But as more and more clusters revealed the same anomaly, it became clear these odd stars were real. They were dubbed blue stragglers, stars that appear to lag behind in the aging process, straggling on as bright blue anomalies among faded companions. The puzzle was clear. How could these stars still shine with such youthful vigour? One theory paints a dramatic picture of stellar collisions. In the dense heart of a cluster, two older, dimmer stars might crash together and merge into a single new star. This reborn star could carry the combined fuel of both, blazing hot and blue, as if it had been given a new life. In essence, the collision would erase the old age of the stars involved, creating a rejuvenated star, hiding among its aged kin. Another scenario is less violent, but equally intriguing. A secret transfer of life from one star to another. Imagine a pair of stars born together, one slightly larger than the other. Over time, the larger star begins to swell and evolve, but instead of dying alone, it starts spilling its gas onto its smaller companion. The smaller star greedily accretes this fresh fuel. With the extra hydrogen added to its core, it effectively turns back the clock, burning hotter and brighter than it otherwise would have. The donor star, having poured its life essence into its companion, becomes a withered shadow of itself, while the recipient glows blue and renewed. Both explanations, cosmic collisions and stellar vampirism, result in the same outcome, a star that appears far younger than it truly is. In either case, the blue straggler is essentially cheating the natural order. It sidesteps the usual timeline of birth, youth, and death by acquiring a new lease on life. In a sense, it's a stellar resurrection, a second youth granted by unconventional means. To an outside observer, it looks like a youthful rebel in an ancient community, but behind that blue glow lies a complex, perhaps tumultuous history. For years, blue stragglers were a riddle that challenged our understanding of stellar evolution. They forced astronomers to consider that stars are not isolated, unchanging points of light, but can profoundly influence each other's fates. By studying these cosmic oddities, scientists glean clues about star cluster dynamics, how tightly packed stars might collide or swap material. Each blue straggler is a living record of an extraordinary event, a cosmic merger, or a parasitic siphoning that kept a star young against the odds. Still, mysteries remain. Are all blue stragglers made the same way? Or do some hide origins we have yet to imagine? In the end, these stars teach us humility. Even something as fundamental as a star's age can deceive us. And age is not the only thing a star can disguise. Deep within their burning cores, stars are forging elements and reshuffling their contents. Sometimes, What we find inside a star is just as confounding as what we see on the outside. There is a poetic aspect to these blue stragglers. They hint that in the grand scheme of the cosmos, even stars might find a way to be reborn or refreshed. It challenges our sense of cosmic order, making us wonder what other tricks stars have up their sleeves. These apparent youthful interlopers tell us that a star's story can be more convoluted than a simple arc from birth to death. It's a humbling reminder that when we gaze into a star cluster, the points of light we see may carry hidden histories we can scarcely imagine. Deep inside a star's core, temperatures soar to millions of degrees. In such an inferno, delicate elements like lithium cannot survive for long. Lithium, a soft, silvery metal on Earth, is a fragile flower in the furnace of a star. It's easily destroyed by the intense heat. By the time a star like our Sun has grown old and swollen into a red giant, we expect it to have virtually no lithium left in its makeup. This is why astronomers were so surprised when they discovered some giant stars that were rich in lithium. It was the last thing anyone expected to find in these stellar elders. Imagine peering into the spectrum of an aging star, essentially its chemical barcode, and finding the clear signature of lithium standing out. It was as if someone had found traces of a cool, rare substance inside a blazing kiln. The discovery posed an obvious question. How did that lithium get there, and why hadn't it been destroyed long ago? These stars weren't just slightly above normal in lithium. Some carried dozens or hundreds of times more lithium than typical giants. Only about 1 out of 100 giant stars showed this oddity, making them both rare and precious to study. Each of these lithium-rich giants became a cosmic detective case, inviting researchers to figure out what unusual event might have happened in the star's life. One hypothesis suggests that these stars somehow manufactured new lithium deep inside themselves. Normally, any lithium created in a star's interior would be quickly destroyed, unless it could be transported to cooler layers before it burns up. Scientists have theorized a special chain of reactions, often called the Cameron-Fowler mechanism, where a star undergoing a brief burst of helium fusion could create lithium and dredge it up to its surface. If true, this would mean the star effectively gave itself a chemical makeover late in life, spraying its outer layers with freshly forged lithium. Another possibility is more external. Perhaps the star acquired lithium by devouring something rich in it. Imagine a giant star expanding and swallowing one of its own planets. A planet that, like some youthful stars, still held lithium in its rocks or atmosphere. As the planet is digested, it could deposit its lithium into the star's outer layers, briefly spiking the star's lithium content. In this scenario, the lithium spike in the star is a telltale sign of cosmic cannibalism, a star feasting on its offspring. Both ideas, internal creation and external ingestion, might play a role, and it's possible that not every lithium-rich star got its bounty the same way. However, even with these theories on the table, the lithium puzzle is not considered fully solved. Astronomers continue to hunt for clues, maybe a subtle tell in the star's light, or a correlation with other unusual traits. The thrill lies in the chase. Each new lithium-laden star discovered is another piece of a puzzle that spans nuclear physics and planetary science all at once. Curiously, lithium is an element that bridges the story of stars and the story of the universe itself. Apart from hydrogen and helium, lithium is one of the few elements forged in the first minutes after the Big Bang. Cosmologists predicted how much lithium should have been made, but when we look at the oldest stars, the numbers don't quite match. This cosmic lithium problem has puzzled scientists for years. Now, these lithium-rich giant stars add a new twist. showing that stars can create or collect lithium later in life in ways we hadn't anticipated. In a way, the lithium puzzle connects the dawn of time with the present-day lives of stars, a thread of mystery running through cosmic history. In confronting the lithium puzzle, we see how stars can hide unexpected secrets in their makeup. These discoveries remind us that even a star's very substance can defy our expectations. And stars don't only confound us with their composition, they can also challenge us in how we use them to navigate the cosmos. For generations, certain stars have been our cosmic lighthouses, guiding our measurements across space. What happens then, when those very lighthouse stars start sending mixed signals? The next mystery takes us into that unsettling territory. In a way, the lithium puzzle is an allegory for the surprises nature holds. A tiny trace element, easily destroyed, ends up being a crucial clue that something unexpected is happening inside stars. It's almost ironic. Lithium, which we use in batteries to power our modern lives, also powers a mystery about the lives of stars. This element ties together the story of the early universe and the inner workings of giant suns, reminding us that even small things can play significant roles on a cosmic stage. For generations, a special kind of star has acted as a cosmic measuring tape for astronomers. These are the Cepheid variable stars, giants that rhythmically brighten and dim, each with a steady, reliable beat. Over a century ago, an astronomer named Henrietta Swan Leavitt uncovered something remarkable about them. Studying Cepheids in distant star clusters, she found that the longer a Cepheid's pulsation period, the brighter it truly is. This discovery meant that if you measure how fast a Cepheid star pulses, you can infer its intrinsic luminosity and thus estimate its distance. Cepheids quickly became precious beacons for mapping the universe. In the 1920s, Edwin Hubble identified Cepheids in the Andromeda galaxy, and using Leavitt's period luminosity law, determined that Andromeda was far outside our Milky Way. That moment revealed that our galaxy is just one island in a vast cosmic sea of galaxies. Since then, Cepheids have been our trusty mileposts, helping gauge the scale of space and the rate of the universe's expansion. Thanks to these stellar lighthouses, astronomers built the first accurate scales of the universe. Cepheids helped reveal that our galaxy is just one of many, and they provided the first step in measuring the vast expansion of the universe itself. By comparing Cepheid distances to faraway galaxies with the speed those galaxies are flying apart, scientists calculated the Hubble constant, the rate at which the cosmos is stretching. For a long time, the numbers seemed to line up neatly, reinforcing our trust in these stars as dependable guides. But as our measurements have grown more precise, a worrisome discrepancy has emerged. When we use Cepheids to measure distances and thus infer the universe's expansion rate, we get one answer. When we use a completely different technique, observing the faint afterglow of the Big Bang and other cosmological markers, we get another answer. The two results don't quite agree, and the difference isn't tiny. It's significant enough that something seems amiss. This conundrum is known among scientists as the Hubble tension, named after the cosmic expansion rate that's in question. It's as if we have two clocks telling slightly different times, and we're trying to figure out which one is correct, or whether they both are, in a sense, and our understanding of time itself needs adjustment. One possible culprit could be the Cepheids, or our interpretation of them. Perhaps these stars are not as uniform as we assumed, or subtle factors like their metallicity or environment are skewing our measurements ever so slightly. On the other hand, the fault might not lie with the stars at all, but with our cosmic framework. Some experts whisper that new physics could be lurking. that maybe the nature of dark energy or gravity behaves slightly differently than we think, affecting those distant observations. For now, it's an open question that cuts to the core of how we measure and comprehend the universe. Researchers have been meticulously recalibrating the Cepheid yardstick. They use nearby Cepheids, whose distances we can measure directly with parallax, essentially geometry, thanks to space telescopes like Gaia. They examine Cepheids in different environments, in the Milky Way, in neighbouring dwarf galaxies, looking for any subtle differences. So far, Cepheids seem to be holding up well as standard candles, yet the tension in cosmic measurements persists. This hints that the solution might lie not in the stars themselves, but in new physics, or an unexpected wrinkle in the universe's early history. The Cepheid anomaly, these conflicting distance indications, has become one of the most pressing mysteries in astronomy today. It's a reminder that even our tried and true cosmic tools can surprise us. Imagine thinking you had a perfect map, only to find that one of your compass points may be off by a few degrees. That is the situation astronomers face, recalibrating our cosmic compass and wondering if something fundamental in our cosmological model needs rethinking. All because some twinkling stars do not line up with expectations as neatly as we hoped. While scientists debate the meaning of this Cepheid conundrum, the universe offers puzzles of a more tangible sort as well. Not just lone stars, but stars together in systems can behave in baffling ways. If single stars can mislead our measurements, imagine the surprises that await when 2 or 3 stars dance in close quarters. In fact, some multiple star systems seem to challenge the very rules of orbital stability, as if gravity itself is performing a delicate, improbable balancing act. The Cepheid conundrum is a sobering reminder that in astronomy, even our most trusted tools can reveal new uncertainties. It is both disconcerting and exhilarating. Disconcerting, because something we thought we understood now raises questions, and exhilarating, because it means there is more to learn. Moments like this keep astronomers humble. We are reminded that the cosmos still holds its secrets close, and we must continually refine our cosmic yardsticks. Ultimately, such anomalies push science forward, nudging us to look deeper and question more boldly. Gravity usually prefers simplicity. 2 stars can orbit each other gracefully, but throw in a third, and things get complicated. In fact, a large fraction of the stars in our sky are part of multi-star systems, yet they tend to arrange themselves in ways that avoid chaos. In a typical stable trio, 2 stars will cling tightly in a close orbit, while the third circles at a much larger distance. This arrangement, like a small couple dancing while a lone partner watches from afar, keeps things relatively orderly. Deviate from this setup, and the gravitational dance can become chaotic, often flinging one star out or causing a collision over time. Our nearest stellar neighbour, Alpha Centauri, exemplifies a well-behaved triple. There, 2 stars, not unlike our Sun, orbit each other at a moderate distance, and a third, much smaller star, Proxima Centauri, circles them far away. This hierarchical structure has kept the system stable for eons. But not all star families are so well-mannered. That's why astronomers were amazed to find systems where multiple stars are locked in orbits so tight, it seems almost impossible that they coexist. Imagine 3 suns all orbiting each other within a space no larger than our solar system. In one such system discovered not long ago, 2 stars whirl around each other in less than 2 days, while a third star circles that pair roughly every few weeks. All 3 are squeezed into a region that, in our own solar system, would comfortably fit well inside Mercury's orbit. By all conventional wisdom, such a configuration should be unstable. Any slight tilt or irregularity, and the close-knit trio would fling itself apart. In the case of this record-setting triple star, it appears they maintain stability by orbiting in nearly the same flat plane, like three marbles rolling on the same disk. This alignment keeps their gravitational tugs in a delicate equilibrium. But even then, astronomers suspect this balance is temporary, a precarious harmony that may last only a few million more years before the dance ends in disaster, perhaps with two stars merging in a brilliant supernova. Sometimes, the anomalies are not obvious until we look very closely. One seemingly normal triple star system defied all attempts to calculate a stable orbit. The timing of eclipses and the tug of gravity just wouldn't line up with any scenario of three stars alone. After much head-scratching, the best explanation scientists could propose was startling. Perhaps there was a hidden fourth star lurking in the mix, its effects masquerading as part of the triple. In other words, we might have been watching a pair of binary stars doing an intricate, perfectly timed dance that only gave the illusion of an impossible triple. If that idea sounds far-fetched, it shows how desperate astronomers can get when faced with such a conundrum. Nature, it seems, had concocted a celestial puzzle where our straightforward models just didn't fit. Triple and quadruple star systems push the limits of what we expect gravity to handle. They hint that these stars may have formed in crowded environments, perhaps siblings born in a tight cluster, or that they're survivors of past chaos, the ones that didn't get flung away. There's even speculation that some star trios started out with a fourth member that is now missing. Maybe one star was ejected into the void or swallowed by a companion, leaving behind an odd-numbered assembly. In one unusual triple system, clues suggest that a fourth star might have been gobbled up during a close encounter, which would explain why the remaining three are in such a strange configuration. It's a stark reminder that these systems are not static. They have histories, sometimes violent ones, written in their present arrangement. These complex multi-star dances underline how dynamic and sometimes ruthless the cosmos can be. When gravitational relationships become unstable, something often gets thrown out or destroyed. It might be a star sent hurtling off into space, or perhaps a smaller victim, like a planet, that gets cast away from its family star. Indeed, not all planets have stars to call home. Some wander alone through the galaxy's darkness, and it's to these drifters that our journey now turns. It's awe-inspiring to realize how nature finds ways to choreograph these complex dances at all. Most of the time, gravity enforces simple patterns. But here on the fringes of stability, we see how delicately balanced and transient cosmic arrangements can be. These star systems are like tightrope walkers, seemingly defying gravity's pull for a time, yet destined to slip eventually. By observing them, we catch a glimpse of cosmic dynamics at their most extreme, and it deepens our appreciation for the clockwork stability we observe elsewhere. Far out in the dark stretches between the stars, there are worlds without suns. These orphan planets drift through the galaxy in perpetual night, unbound to the warmth or gravity of any star. Imagine standing on one of these lonely worlds. Overhead, no familiar sun rises or sets. The sky would be black, except for the distant glow of countless stars, like an eternal, cold night. Any warmth would have to come from the planet's own core, or perhaps a faint memory of heat from its birth. For a long time, rogue planets were purely the stuff of theory and imagination. Without a nearby star, these wanderers emit almost no light of their own, making them nearly invisible in the blackness of space. But astronomers have grown clever in their search. Sometimes a rogue planet betrays its presence by drifting in front of a distant star, causing the star's light to bend and briefly brighten, a cosmic wink signaling a hidden world passing by. Through such delicate observations, we now know that rogue planets are real. In fact, they might be more common than anyone guessed. Some studies hint that the galaxy could be teeming with these free-floating worlds, perhaps even as numerous as the stars themselves. Astronomers have even managed to capture a few directly with sensitive telescopes, images of faint, planet-sized orbs shining softly in infrared, alone in the dark. They range in size from gas giants, many times the mass of Jupiter, down to perhaps smaller, rocky, Earth-sized nomads, all wandering the interstellar gulf. How do such planets come to be cast adrift? Some likely began life in orbit around a star, forming in the swirling disk of gas and dust like any other planet. But in the early chaos of a young solar system, gravitational scuffles can happen. A giant planet might swing past another giant in a close encounter and get slingshotted away, or a passing star could tug a planet out of its orbit. In those moments, the planet is banished, flung into interstellar exile to wander on its own. Others might have formed in isolation, collapsing out of a cold cloud of gas that wasn't massive enough to ignite into a star. In that sense, some rogue planets could be like tiny failed stars, never quite lighting up, born to roam the galaxy alone. Whether born free or later cast loose, these planets share a common fate. It is an existence in the silent emptiness between star systems, far from any nurturing sun. The idea of planets adrift carries a special kind of melancholy wonder. If such a world has moons, it might still have a little company on its endless journey, a miniature system of its own, a planet with loyal moons trailing along as it glides through the dark. Perhaps beneath thick insulating atmospheres or ice, some of these moons or planets could even retain a glimmer of warmth, an ember of geological activity to stave off the cosmic cold. We don't know, and that mystery adds to their allure. If solitary wanderers highlight loneliness in the cosmos, there are also stories of unsettling intimacy. Elsewhere in our galaxy, some stars cling to companions in dangerously close embraces. Instead of drifting apart, these stars draw ever closer, one feeding on the other's material like a cosmic vampire. It's a stark contrast, not isolation, but a fatal kind of togetherness, and it's our next enigma to explore. There is a poignant loneliness to the idea of a rogue planet. Cut off from the light of any sun, such a world underscores the vast isolation that can exist in space. Yet there's also a strange beauty in it, a planet untethered, forging its own path through the galaxy. It expands our perspective of what a solar system can be, reminding us that not all worlds bask in starlight. In the darkness between the stars, even isolation becomes part of the cosmic tapestry, a piece of the grand story of how objects travel and evolve over billions of years. In the cosmic drama of binary stars, sometimes one star becomes the predator and the other the prey. This process is often dubbed stellar cannibalism, and it can take many forms. Essentially, it occurs when one star siphons gas from its companion, drawing the very life essence of its neighbour onto itself. It's a scenario as eerie as it sounds, a star feeding on another star, bit by bit. We caught a glimpse of this earlier when considering the blue straggler stars. Those unusually youthful stars could very well be the result of a star stealing mass from its partner to rejuvenate itself. By guzzling down fresh hydrogen from a companion, an aging star can rekindle its nuclear fires, appearing younger and hotter than it should be. In effect, it turns back the clock on its stellar lifespan at the expense of its partner, which is left drained and prematurely aged. In the quiet exchanges of matter between two suns, one star's loss truly becomes the other's gain. A classic example of stellar vampirism is found in the constellation Perseus. There lies Algol, known for centuries as the demon star, because it visibly dims and brightens every few days. Today, we know Algol is not one star, but two in close orbit, regularly eclipsing each other. But Algol also presented a riddle. The star that appears brighter is actually less massive and young-looking, while the dimmer star is more massive and evolved. This is the opposite of what we expect. Heavier stars normally age faster and die sooner. The solution to Algol's paradox was a dramatic act of cannibalism. Over time, the originally bigger star in Algol poured much of its matter onto its companion. The once smaller star grew in mass and brightness, becoming the apparent master of the system, while the donor star was left stripped of its youth and vitality. What the ancients saw as a demon's blinking eye was, in truth, a cosmic vampire story playing out in the night sky. Stars can not only steal from each other, they can also consume lesser prey, like planets. In the red giant phase, a star swells to hundreds of times its original size. Any nearby planets can be enveloped and digested by the expanding star. Astronomers suspect that some chemical peculiarities in giant stars, like unusual abundances of certain elements, may be the smoking gun of planet engulfment. It's a fate that likely awaits some of our own solar system's planets when the Sun becomes a red giant in the distant future. Mercury and Venus, at least, will slide into the Sun's bloated atmosphere and be consumed. The Sun will literally dine on its children as it transforms. A reminder that in the life cycles of stars, creation and destruction often go hand in hand. In more extreme cases, the cannibalistic behavior can lead to spectacular outbursts. Consider a binary system where one of the stars is a tiny but dense white dwarf, the remaining core of a star that has already died. If this white dwarf orbits a bloated red giant, it can act like a parasite, pulling gas from the giant's outer layers. The gas swirls down onto the white dwarf's surface, forming a hot, dense shell. When enough has accumulated, it can ignite in a sudden thermonuclear blast on the dwarf's surface, creating a nova, a stellar eruption that causes the system to brighten dramatically for a time. What we witness as a new star appearing in the sky, the word nova means new, is actually an age-old star indulging in a fresh meal and momentarily catching fire from the feast. If the white dwarf continues to gorge on its companion's matter without relief, an even more dramatic fate awaits. The dwarf may reach a critical mass and detonate completely in a Type Ia supernova, destroying itself and potentially its partner. It is the cosmos's ultimate expression of overindulgence, a star that ate until it burst. Such explosions are among the standard candles we use to measure cosmic distances, tying back to how even destructive acts become tools for cosmic understanding. After witnessing stars savagely consuming their neighbours, we turn to a more delicate mystery. Not all surprises come from violence. Some creep in quietly, as subtle changes in a usually dependable pattern. Consider those Cephid stars again, the ones that beat with such reliable periods that we use them to gauge distance. What if one of those cosmic clocks began to tick off beat? It turns out that too can happen, and it's an enigma of a very different kind. There's a stark lesson in these vampiric star tales. They remind us that in the cosmos, creation and destruction often go hand in hand. One star's renewal comes at the cost of another's depletion. One star's brilliant finale might be triggered by the presence of a companion. It's a dramatic interplay, almost like a cosmic morality play about dependency and sacrifice. Beyond the scientific curiosity, there's a visceral awe in knowing that stars can so intimately affect one another's fate, bound together in light and loss. Cepheid variable stars have often been compared to reliable timepieces. Once set in motion, their cycles of brightening and dimming are so regular that we count on them as cosmic clocks. Their steady cadence is a comfort in the volatile heavens. However, even these stellar clocks can drift off beat, and when they do, scientists take notice. Polaris, the North Star, is one such cepheid. For ages, it has been a nearly constant friend in the night sky, barely changing in brightness to the naked eye. Indeed, to navigators and explorers, Polaris's steadiness has been a guiding comfort. Only with telescopes and precise instruments did we learn that Polaris does indeed pulse, ever so gently, its brightness oscillating over about 4 days. What stunned astronomers was that this oscillation began to change in the last century. The swings in Polaris's brightness started shrinking. By the late 20th century, it seemed Polaris was hardly varying at all anymore, as if its heartbeat were fading out. Then, in an unexpected twist, Polaris's pulsations began to grow again. Into the 21st century, observers noted that its once diminished rhythm was amplifying. It was as though the star had paused and then decided to resume a former life. Even the timing of its pulses has drifted slightly over the decades, like a clock running a touch fast or slow as it ages. Such a rapid change is extraordinarily hard to explain because stars are not known for sudden transitions on human timescales. Whatever Polaris is doing, it's doing it faster than any theory would have predicted for a Cepheid star. Scientists have proposed a few ideas. Perhaps Polaris is in a brief evolutionary phase. Maybe it's crossing a threshold in its life where its pulsation mode is shifting. Some suggest that Polaris might be a special case, a Cepheid on its first journey through the instability strip, which could make its behavior less predictable. It's also possible that interactions with its close companion stars, for Polaris is part of a multiple star system, might subtly influence its pulsation. At present, none of these explanations is confirmed, and Polaris continues to keep astronomers guessing. Polaris is not the only Cepheid with peculiarities, but it is the most prominent. Other Cepheid variables have shown gradual changes in their periods, usually a slow lengthening or shortening over decades, which we generally attribute to the star's natural aging. But rarely do we catch one in the act of a sudden shift. It's akin to hearing a familiar song skip a beat unexpectedly. In those moments, we are reminded that even our cosmic metronomes can hold surprises. These drifting stellar rhythms underscore a theme we've seen before. Even the most steadfast cosmic phenomena can falter. From variable stars to Cepheids, the universe has a way of inserting a subtle syncopation into its music. Now, we turn to a mystery not of timing, but of the light itself. Situations where stars give off a glow that doesn't quite match the heat we expect. In the next puzzle, the very radiance of stars raises eyebrows, hinting at hidden mechanics at work. Watching Polaris's fickle heartbeat reminds us that nothing in the universe stands completely still. Even the stars we count on as constants are slowly evolving, changing in ways that only careful watching can reveal. There's a quiet thrill in that realization. The cosmos is dynamic on every level. The North Star's subtle shift doesn't diminish its reliability for navigators, but it adds a layer of depth to its character. It's as if we've learned a secret about an old friend. In the grand scheme, these Cepheid clock drifts encourage us to keep listening to the stars with patient attention, because they may have more to say. Stars shine primarily because they are hot. Their brilliant light is the glow of immense heat generated in their cores and radiated from their surfaces. But nature has a way of complicating even this simple picture of starlight. Sometimes we find stars emitting radiation that doesn't square with their surface temperatures, a kind of glow that seems to come without the expected heat. Take our sun, for example. Its visible surface, the photosphere, is about 5,500 degrees Celsius, certainly hot by any standard. Yet if you move just a few thousand kilometers above that surface into the sun's corona, the temperature soars to over 1,000,000 degrees. It's as if stepping away from a fire made you suddenly much hotter instead of cooler. We can actually see the sun's mysterious corona during a total solar eclipse, when the moon covers the blinding disk and a pale halo of light appears. That wispy crown is the 1,000,000-degree plasma glowing around the sun. This baffling solar paradox, a relatively cool surface beneath an extremely hot atmosphere, has challenged scientists for decades. The sun's corona shines in high-energy X-rays and ultraviolet light, a glow of searing plasma, while below it, the sun's surface glows only in visible and infrared. The source of the corona's heat is still not fully understood. One leading idea is that the sun's magnetic field lines, which twist and snap above the surface, might be hurling energy into the corona, a bit like cracking a whip and sending a wave down its length. Another idea involves waves in the plasma, called Alfvén waves, that carry energy outward from the roiling surface and deposit it in the corona. Bit by bit, researchers are gathering evidence for these theories, but the complete answer remains elusive. And it's not just the sun. Other stars also show signs of mysterious high-energy glows that defy simple explanations. Many stars have coronae like the sun's, often even hotter in proportion to their surfaces. Some young stars shoot out powerful X-ray flares, far more energetic than their surface heat alone could produce. These flares can outshine the star's normal light in certain wavelengths, momentarily making a relatively cool star seem like it has a raging furnace on its surface, except the furnace is in the star's magnetic atmosphere, not at its visible surface. Even the smallest of stars, and objects barely qualifying as stars, can surprise us with strange light. Brown dwarfs, for instance, are cool, dim bodies, often called failed stars, because they aren't massive enough to sustain hydrogen fusion. You might expect them to be inert and quiet. Yet astronomers have detected brown dwarfs emitting bursts of radio waves, a telltale sign of magnetic activity like an aurora. In such cases, we have a world only a few hundred degrees warm lighting up the radio spectrum with energy. It's a bit like finding a block of ice that glows in the dark, certainly not due to its temperature, but because of another hidden process at play. All these cases, where a star's radiance doesn't neatly align with its thermal state, remind us that starlight can be driven by more than heat alone. Magnetism, shock waves, stellar youth and old age. Various forces conspire to produce these anomalous glows. They are subtle clues that stars are dynamic, layered beings, with secrets hiding in plain sight in the light they give off. Having delved into so many mysteries among the stars within our Milky Way, we now set our sights further afield. It's time to journey toward the fringes of our galactic home, where the familiar gives way to the unknown expanse beyond. What these phenomena ultimately teach us is that stars are not just simple balls of fire. They are intricate systems with magnetic fields, winds, and layers, almost like living organisms with internal weather and activity. The phrase "glow without heat" captures a sense of wonder, that nature finds unexpected pathways to shine. It's a reminder that when we look up at the stars, much of what's happening is invisible to us, energetic dances of particles and fields that we only glimpse through peculiar clues. Every star, even the most ordinary, may harbour extreme conditions in some hidden layer, challenging us to unravel its full story. We drift outward, leaving behind the bustling stellar neighbourhoods towards the quiet outskirts of the Milky Way. Out here, the stars thin out. The bright band of the galaxy's heart softens, and the darkness between worlds deepens. It's a lonely, liminal space, not quite intergalactic void, but far from the galactic core's glow. If one could stand at the galaxy's edge, one might see the sweep of the spiral arms from a distance, with the core as a faint haze behind, and the infinite black of intergalactic space ahead. The nearest other galaxy, Andromeda, would be just a tiny, dim cloud in the sky, a reminder that beyond our island universe lie countless others. Yet even in this remote frontier, mysteries persist. The outskirts of our galaxy hold their own puzzles. The Milky Way's disk is not perfectly flat, but warped and wavy, as if something unseen is tugging at it. Perhaps the gravitational nudge of orbiting dwarf galaxies, or the subtle pull of dark matter. Streams of stars wind through the halo, remnants of smaller galaxies long ago devoured by our own. Wisps of gas, high above the plane, race at unexpected speeds, hinting at forces and past interactions we do not fully grasp. This boundary realm between galaxy and intergalactic space is a cryptic ledger of our galaxy's history, written in faint stars and ghostly motions. Gazing outward from the edge, one senses that the Milky Way is not an island unto itself. Orbiting around us are diminutive companion galaxies, like the Magellanic Clouds, faintly visible from Earth's southern hemisphere, and dozens more even smaller satellites. Their gravity, along with the mysterious halo of dark matter enveloping our galaxy, constantly tugs and distorts the Milky Way's form. The warps and streams we see at the edge are whispers of past encounters and ongoing interactions with these galactic neighbours. Even out here, where things seem quieter, the story of our galaxy continues to unfold in subtle motions and faint structures. Standing at the rim of the Milky Way is a bit like standing on a shoreline at night. Behind us are the lights of our galactic city, growing fainter, and ahead is a vast cosmic ocean of darkness, speckled with the faint glow of other island universes. It's a threshold of sublime scale. From here, the questions multiply. What lies in the space between galaxies? How does our Milky Way interact with the immense void and its sparse inhabitants? The journey onward will carry us into that great unknown, step by step, peeling back the layers of mystery that lie beyond our galactic home. As we conclude this leg of our journey, poised on the boundary of our galaxy, the vista is both tranquil and tantalizing. The Milky Way's mysteries have carried us from flickering stars to ghostly coronas, and now to the silent fringe of its spiral arms. Here, on the brink of intergalactic space, one chapter of exploration ends, and another begins. The rim of the galaxy is not a hard edge, but a threshold. Beyond it lie the vast reaches between galaxies, with riddles of their own. Our cosmic journey will continue, moving outward into that great unknown, where new wonders surely await in the darkness between the stars.